Okay, let's get started. By the way, could people hear the sound on that?
Yes.
Good. Okay, so I want to start with a bit of an activity. I'm going to ask a question. Well, actually, I'm going to give a follow-up and then I'm going to ask a question. And I want someone to answer that question, but by answering it, they commit themselves to attempting a follow-up question, which is a puzzle based on the first question. So when I was doing one calculus 2 recitation a while ago, I put on my quiz, the first quiz, question. Why does the moon wax and wane? And I explained that this means the lunar cycle. So in other words, why do we see the moon changing cycles as it goes through a 28-day period? And most of the answers that I got were actually wrong. It was about 50-50 splits. So then I posed the question, why does the moon wax and wane? Why are there lunar cycles? So I now would like a volunteer, but by answering, you are committing yourself to answering the follow-up. Also, does anyone not understand the question?
I mean, essentially, the moon waxes and wanes in proportion of like how much in front of the sun it is, and is a reflection of it, and also how like the moon orbits around the Earth, right?
Right? So at a given time, if the moon is half full, why is it that it's half full?
It's because in its a rotation, it is like the dark side of the moon is half full. Or like we see the other half of the moon, which is always labeled as the dark side halfway through. Whereas if we had a full moon, we see very little of it.
Okay, well, I think that you're getting that accurately. An interesting point is that we always actually only see one surface of the moon, but that surface isn't always bright or dark. So the name dark side of the moon is a bit of a misnomer because the dark side of the moon, well, the back side of the moon, the one that we don't see, is light as frequently as it is dark.
Oh.
In fact, the face of the moon is locked towards the Earth due to a phenomenon called tidal locking. But anyway, ignoring that the moon doesn't, we only see one face of it, if we see that it's half lit, it's because, well, half of the moon is lit somehow, right? But
Yeah.
the part that's lit may be on the backside of the moon, right? So that was your answer.
Yeah.
Okay, so here's the follow-up question then. The first part is not as much a logical puzzle as the second part is. So why do solar eclipses happen?
Solar eclipses are when, if I remember correctly, the moon is directly blocking the sun, right? Or like our point of view of it.
Right.
So it has the appearance of it being entirely black.
Right,
Or
very good.
it blocks the sun, yeah.
So, okay, so now here is the actual follow-up question.
All right.
Imagine that a solar eclipse is about to start. So the sun is completely uneclipsed at this point.
Mm-hmm.
In 2 minutes, the eclipse is going to start happening. What does the moon look like?
No. Well, don't solar eclipses happen when the sun is out? So like the moon is barely visible in the sky, right?
Well, a lot of the time, I think, well, actually, there was a full moon a few days ago, so it doesn't apply, but 2 weeks ago, for example, you can usually see the moon in the sky at the same time. Sometimes they're antipodal, but no, you can still see the moon in the day sky. But that's a separate question. in this specific circumstance, what does the moon look like?
If I were to guess, probably a new moon. Like it's completely black.
Empty. Yes. So the answer then is, well, actually justify that here.
Because I think, like, my theory would be like, for it to be completely black out, you couldn't see any reflection of the sun through it. So something of complete darkness would have to block the sun for it to eclipse.
Right, because after all, you have the Earth, the moon, and the sun in a line, right?
Yeah.
And if they're perfectly aligned, then what side of the moon is going to have light shining upon it? The side
The back side of it. Yeah.
Yes, exactly. Right. So in one word, the answer is nothing. You see nothing, and then the eclipse begins to happen. Actually, on Saturday, Saturday after midnight, so on Sunday, there was a lunar eclipse, but it was a penumbral lunar eclipse. If you draw lines from the edges of the sun to the Earth, they're sufficiently non-parallel that there are two different regions of shadow. And the one which only has half of the light blocked off, its apparent magnitude changes very little. So it's actually very hard to see a penumbral eclipse. But another interesting point is then whenever there's a lunar eclipse, so the Earth blocks the sun's light from hitting the moon is full, right?
Mm-hmm.
So that's also another interesting observation. So for example, sometimes the media report there's a lunar eclipse, it's a full moon lunar eclipse, but that's a tautology because every single lunar eclipse is a full moon eclipse.
Yes.
Right. Okay, good. So that was an exercise, but that was a bit of a puzzle. So here's then, okay, so now I'm actually going to begin the lecture in earnest. By the way, does anyone have any questions about that? Oh, I'll say I'll give a speech about asking questions and about the general tone of this class a while later. But okay, so let's get into this. Oh, also, actually, I can mute everyone's mic. Can everyone please mute themselves? Here we are. Okay, if you want to ask a question, unmute yourself. Okay, so here, we're launching into lecture in earnest. So, in answer to this question, if you look at the moon then, when in lots of situations at night, for example, you see the moon. Let's say you go out at night and you look at the moon. You can ask the question, where is the sun? It's dark outside, but where is the sun? By looking at the moon, you can actually point to the location of the sun. And this brings up the following quotes. Bright in the night with the gift of his light, round the earth she is ever erring, evermore letting her gaze turn towards Helios's rays. These are lines from a poem by Parmenides called The Way, or On Being, rather. And I saw these lines in a poem by in an essay by Karl Popper on Parmenides. And Popper begins the essay by remarking that he read Parmenides first when he was 14 or 15. And after reading these lines, for the remainder of his life, whenever he went outside and looked at the moon, he would always figure out exactly how it is that the moon's gaze pointed towards the sun. And so this is an interesting puzzle that you can do. Right now, the moon is mostly full, but in a few days, the configuration will be slightly more interesting. And you can almost exactly point to where the sun is located, even if the sun isn't visible, so long as that you can see the moon. As a much more difficult problem that you can't do directly, you can also tell what season it is up to 6 months apart, just from the picture of the sky with the moon in it, if you can tell angles. Right. So that's a line that happens in Parmenides' essays. Now, who is Parmenides? Well, Parmenides is a Greek philosopher. And in this work on being, it's a poem, and it involves a stand-in for the author, so some character. Some character is taken away and raptured to the place of dwelling of a goddess, the goddess of justice. And the goddess of justice says to him, I will tell you the way that things are. People, usually, they see things and their perceptions are incorrect. But I am a goddess, I stand above mortals, and I know the truth. And I'm going to tell you the truth. But I'm not going to tell you the truth dogmatically. You don't have to believe me. You don't have to take my word for it. What I'm going to do is I'm going to tell you the truth in a very convincing way. And you are going to be absolutely certain that what I say is facts if you apply reasoning carefully. So it is not a dogmatic account of a goddess. It is a logical argument provided by a goddess that on its own should be absolutely compelling. And so the goddess begins by saying that there are two central points to this discussion. The first is that she will argue that senses cannot be trusted, and that what one should trust is reason over senses. And only by reasoning can you come to the truth. The second point after this is, well, she starts with a few hypotheses, like things that are, and that things that aren't, or what is, and what is not, cannot be. That's the usual way to state it. And then, starting only from this assumption, she continues reasoning, and she makes the conclusion that everything is one, all space is homogeneous, nothing differs, nothing changes, the world is full, all of existence is a sphere. The sphere doesn't change. The perception of change is only an illusion, and you can easily, logically see from arguments that nothing that we actually experience is real. And this is presented in clear logical form. And this is utterly compelling. Now, in Karl Popper's context for why Parmenides wrote such a poem, he notes that Parmenides was a very accomplished astronomer as well. And he is credited for many things. First off, the fact that the Earth is spherical. Well, Parmenides' poem survived, but his work is the first to mention in our historical record the fact that the Earth is spherical. It's probably not due to him, but he's the first one who's recorded the fact in what survives. Then there are things like the morning star is the evening star, which doesn't mean much to us in present day. I mean, yes, it does, but it's not immediately clear to you what that sentence is actually about. And then finally, an explanation of why the phases of the moon are the way that they are. Prior to that, the most compelling explanation put forward was by Heraclius. And what he said is that the moon and the sun are half hemispheres. They're spheres like bowls, and the bowls have fire in them. And sometimes the bowls of fire turn around and obstruct part of themselves. And Parmenides, when you see this picture of why is the moon has phases? Well, the moon has phases because half of the moon is illuminated at any given point in time. But if you just imagine a sphere in which half of it is illuminated, you can look at the sphere from lots of different positions. If you're looking at it from the back, the non-illuminated side, you see nothing. If you're looking at it from the side that's completely illuminated, you see everything. And then in between, you have phases. So it's the rotation that causes this perception. Now, what was the mistake? Why was it that people thought it was a bowl of fire? Well, that's because they see something and they see lights and they see this thing. And it's associated, you have this association that because there's light on it, something exists. In other words, some sort of equation of light with being. And this mistaken association of if you see something, it's there. If you do not see something, it isn't there, is what led to the error. Now, what is light, according to Parmenides? I mean, does light leave force? Is light some corporeal thing that you can touch? Well, barring modern ideas like photons exist, no, it really isn't. You can't feel light. Okay, I know there are several things that you can say about it, but that argument stood ground at the time. And so the mistake was thinking that light exists when light doesn't really exist. And the only reason we think light exists is because we perceive things. And our perception leads us to believe that certain things exist and that certain things don't exist. So in fact, it was senses that led to this incorrect view of the sun, whereas reasoning, pure reasoning, will tell you that it's the other way around. And Popper says that Parmenides overgeneralized this. He took all of these things in which senses were the culprits, and he said, you know what? Very radically, we can't trust senses. If we go pure, very radical reason, what can we conclude? Well, we can conclude that nothing that we experience is real and that nothing changes. Now, you may say, okay, well, sure, you can write that. But is it to be believed, or are other people going to take it seriously? And the fact is, yes, other people took it seriously. In fact, this was one of the clearest arguments that was written at the time. And Parmenides' dates are around 500 BC. And by the way, he is known as an Eleatic philosopher. I actually don't remember what the city is called. It's Eleaios or something of the sort. But the adjective from the city name is Eleatic. And you have philosophers like Zeno, where Zeno's paradoxes of motion, he was a student of Parmenides. And then there are several others. So that Eleatic school was the school that produced all of these contradictions about motion.
I have a question. Does he predate or does he come after Aristotle?
Oh, he predates Aristotle by a significant extent. You have accounts, for example, Plato. Plato writes Parmenides is the father of us all.
Oh, okay. I was
So
curious.
these are pre-Socratic philosophers. Parmenides is perhaps the most important pre-Socratic philosopher.
Yeah. Okay, thank you.
Right. And right, so at the time, this argument, by the standards of arguments that they had, was utterly compelling. And everyone had to admit that there was no way to find a hole in this argument. It was tight. It was precise. You had no choice but to accept it. And when you get to the state where you have some beliefs about how to argue, you have some beliefs about what makes, what assumptions you can start with. And when taking those beliefs, by a very tight process, you can reach such a conclusion that's so logically unacceptable that everything is an unchanging homogeneous sphere. That's a crisis. How do you reconcile that? It would be easy if you could find some hole in the argument, but no one can. And this is very disturbing. And this, arguably, was the first crisis of knowledge. Now, as a prelude, why would people take it so seriously? Well, we have to talk a bit about Greek society. So almost every single culture in existence, no, that's the wrong statement. Any recorded civilization, any historical record that survives, that gives us a picture of a society, that society will value communication skills and logic and argument in some way, without exception. Humans are social creatures. They like to convince other people of things. And it's not as though Greeks invented arguing in a much stronger sense. And for example, the indigenous people of Greenland are the Eskimos. And in the book that I'm reading, they mention, for example, that Eskimos have song duels. When people have a legal conflict, disputes, the way that they settle the disputes is to invest themselves into having singing battles. This is an actual thing. You can look it up. But, and then there are lots more examples of where honing your skills of communicating with someone are useful. But Greek society was a bit different. Why is this? Well, first off, I can tell you how it was different and why that's important for mathematics. In mathematics, which we haven't gotten to yet, in Greek society, you would have a lot of people organized into very specific research disciplines. So everyone agreed upon some set of rules in which they were working. And people thought, what are the important problems in math? Well, most contemporary mathematicians at the time would agree that these are the most important problems. There was sort of a unanimous agreement on which direction the research program was going in. And the research program was so internally structured that if you looked at the problems that were considered the most important problems of the time, they would not make sense to anyone outside of the research program, in the sense that you could not find it important. You could not care about this problem. A very specific thing is compass and straight edge constructions. You have problems like the problem of trisecting an angle. Well, you can easily trisect an angle if you, for example, well, if you have a ruler and you, or a protractor. If you have a protractor, you can trisect an angle. That's one answer, but that's not a pure answer because protractors only have a finite precision. But if you're working in this very constricted world where all constructions that you can do are by compass and straight edge, then trisecting an angle is impossible, but that could only be proven in the 19th century. And it was a problem that a lot of people worked on and cared about. And seeing that you can do this with a protractor, you may say, well, why is it a problem that people care about? Why do they care about working in the constraints of this theory? And you only care if you're in the theory and you're working with all these constraints, so that when you say something, if all of your math's already wrapped up in there, proving something else within those constraints enriches the rest of existing mathematics. And without that context, you just don't care about the problem because you don't say why, you don't see why you should limit yourself to that. And so once again, Greek society was distinguished in the fact that mathematics, along with almost every single other discipline, organizes itself into research programs where the practitioners of that research program shared a common goal to advance that specific agenda for the subjects. And that's unprecedented in history. Okay, but going back to there, what made Greek philosophy distinct? And this is sort of a sociological explanation. Well, it's because Greek society had a very unique social setup due to this new innovative thing called democracy. Now, democracy was restricted basically to ethnically national, multi-generational land-holding males. So it was the limited form of democratic participation, but nonetheless, decisions were decentralized to the extent that if you could argue and if you could convince people, that skill was more useful in achieving a goal than it would be in other societies. Okay, clarification. These arguments were very public. And the people hearing these arguments would be roughly the same set of people that participated in the democratic process. So time and time again, in a public setting that was very organized and controlled, I mean, you'd have a lot of chaotic arguments, but still, you met at a certain point to argue. And given that it was procedural, and given that winning within the rules of those procedures would let you advance your way, which was something unique to this setup of governments, arguments started to become refined. So for example, if you wanted to just do cheap populism or cut logical corners, make very wide appeals to emotion, if arguing is such a central part of governments, eventually people begin to see through that. And eventually people begin to study, well, how can I convince people better to get my way? And then people start internally looking towards arguments. How do I know something? How can I trust my beliefs, et cetera, et cetera? Now, if you just look at those questions alone and you make some theories about that, that doesn't make mathematics. That doesn't make anything. All of that is just auxiliary to the very important thing. Putting it this way, let's look at how humans understand how to construct things. So the theory of constructing buildings. Now, this is a completely fictional metaphorical story, but you can imagine that people start building a few things. They start building more things and more things, and then eventually, slowly, they increase their skills about what they can build, and then they go for a very, very ambitious project. And then they construct this ambitious public infrastructure project, and suddenly, after you've gotten to that point, the entire thing spectacularly breaks down and collapses. Now, the theory of how to build will immediately get developed very aggressively as people see as to why that happens. It's the crisis that causes the real movements. You have all of this slow progress in where you form some beliefs, and it's only at the moments where you realize, oh no, all of our beliefs are colossally wrong in a very fundamental way. It's apparent to you that what you believe is wrong. For example, if in construction, your building collapsed, that's a fact that's staring you in the face. What can you do about that? And similarly for Parmenides. Parmenides came at a time after maybe 250 years of development of what constitutes rhetoric. And so there was a very good theory of how to argue, and there was also a very good theory of dialectic. Rhetoric is convincing people. Dialectic is the sort of discussion that you have when you want to get to the truth of something. It's the process of figuring out how something behaves, what something is. I remember also that Aristotle wrote, for example, that so with culture originating in the Homeric epics, that Homer even taught the Greeks how to tell proper lies. For example, when Odysseus returns to Penelope, as a merchant, and he says to her that I am a merchant who was, it says my introduction is table, right? Who was at Odysseus's reception some large number of years ago. And in order to prove his claim, he describes what Odysseus looks like. And so had he been a merchant who had been at Odysseus's reception at that time, he would know what Odysseus looks like. So Penelope is convinced that, oh yes, his story checks out. Whereas that's not true. He in fact is Odysseus, he is not this merchant. So that is called I didn't write this down. Well, anyway, A implies B, B therefore A. That's an argument that doesn't work, as we see here. And so this is Homer teaching the Greeks how to tell proper lies, a part of rhetoric. Anyway, apart from that, so you have all of this culture built up. And the important part about any social circumstances that lead things to being built up is that they're purely auxiliary to the moments at which you can land yourself in a crisis. And Parmenides represented the first scientific and philosophical crisis. In fact, if you start at the history of science as a subject, a very good starting point is Parmenides. After Parmenides, people began to look much more closely at what the foundations of a subject are, and became very, very careful, very paranoid about people discovering contradictions in their theory. If you started just saying a theory about something, you'd be very concerned that someone like Parmenides would come around and say, you know what you're talking about? You say you know what you're talking about? Really? Really? Here are some holes in it. Here are holes in your understanding. And in order to avoid that, in order to avoid having a theory develop for several hundred years and then finding out that there are tons of holes in it and that everything needs to burn down, people became very careful about what constituted an argument. And this served really to focus mathematics. So starting from Parmenides, we can look at what Greek mathematics looked like. So now I'm going to switch over. Where is my mouse? Oh, actually, no. Yes, I look at the slide once more. So I'm going to tell you about what Greek mathematics looked like prior to Eudoxus, and then what Eudoxus's contribution was. And this really represents a very tight theory about numbers. And it also represents why you don't, for example, don't need calculus. If you look at Newton's Principia, Principia was released before Newton published his results on calculus. And while there are calculus flavor arguments in it, you can say that the Principia really doesn't use calculus. It's purely geometric. And Newton was able to do this because he read Apollonius. If you read Apollonius, you'll see why you can do almost everything without this, but it's very careful. But this lecture will also give you an idea of how. Now, of course, I'm not saying that you should, but the fact that you can is interesting, and there's something that we can draw from that. For example, well, I'll get to the points after I do this. So let's start with something that represents the ending point of Greek mathematics, Euclid's Elements. This is really all of the theory wrapped up in a book and collected. But some parts of it predates Euclid by far. And if we just look at the starting points that Euclid used, they were really starting points that predated Eudoxus by far. So the book begins with the elements, Euclid's Elements, with several definitions which are somewhat unenlightening. For example, a point is that which has no part. A line is a breadthless extent. Okay, I'm not sure about the wording of that one. And then it goes through several. But then you get to these 5 axioms. So what are the 5 axioms? The first one is to draw a line between points. So if you have 2 points, these constructions are called compass and straight edge constructions. A compass, by the way, is a tool that lets you poke an arrow into a page and then extends the marking point to some point and then draw a circle. So given a center of a circle and some other point, you can draw that as a circle of its radius. That's what a compass lets you do. And then a straight edge is just an unmarked ruler. So you can't measure lengths using it, but you can draw lines. So what can you do with a straight edge? Between 2 lines, between 2 points, 2 different points, you can draw a line connecting them. Now, you can also put a ruler up to that line and extend the line further. For example, draw another 2 points on there, match that up and extend it. So you can also extend lines. That's points 2. Point 3 is you can use a compass. So you actually have access to a compass. So 1, 2, and 3, these axioms, to draw a circle of any center and radius, really represent the fact that you have a compass and straight edge as tools. They don't represent that many assumptions about space. Now, the 2 assumptions that come in about space, and we won't be using these much, although there's a lot to say about them, is that 1, all right angles are equal to one another. Right angles are defined previously, but let's not worry about that. And the other one is the parallel postulates. So not writing it like this, you could say it in a different way, that parallel lines don't intersect, and that any 2 lines which are not parallel intersect exactly once. That's something that's equivalent to the parallel postulates. The actual text says on which side of the angles they intersect. But so ignoring 4 and 5, let's just look at the first 3 axioms which say that you have a compass and straight edge. Okay, now I'm going to switch to drawing mode. By the way, does anyone have any questions? So this is getting somewhere, and the main content of the lecture will start after this. But this should be a part of the lecture which sets the stage for the rest of the course. There is a point that's coming. Trust me on that. Okay, so let's see. What these look like. So for example, given any 2 points, the first axiom says that you can draw, a straight line. I can't certainly, between them. And then the third axiom says that if you have a point and you have a length, so some segments, that using this as the center, you can draw a circle, again, which I certainly can't. I say that before even attempting. Circles are hard to draw. They're very hard to draw. Right. And then after the axioms, there are some common notions. And the common notions, they are actually very important. They roughly say that if one thing is equal to a second thing and a second thing is equal to a third thing, then the first thing is equal to the third thing. Then if one thing is less than another and the second thing is less than the third, then the first thing is less than the third. So they talk about properties of less than and equality, and they establish basic properties about them. If you just think that less than or equal to makes sense, then that captures the common notions. But for example, if you look at the definitions, which I didn't say, you have the definition of a circle, and a circle is defined as, so it's a figure that has a center, and that if you extend a straight line from its center to its boundary, all of these segments are equal. Well, I mean, this segment is not literally this segment, but that tells us what the word equality means. Equality in Greek terms is, there are different types of magnitudes. You can talk about lengths, you can talk about areas, and you can talk about volumes. Now, 2 lengths or 2 line segments are equal if they have the same length. So any radius of a circle is equal, despite the fact that the literal line segments are different. And the final common notion is that the part is greater than the whole. So always, for example, if you have some area, let's say you have a square. A square means a filled-in square, so this is an area. And then you take some smaller square, then you know that that smaller square is smaller than the bigger square because it is a literal part of the bigger square. It's contained inside it. So that lets you see that some things are less than another in a very literal way. Then the theory begins. The first proposition in Euclid is that, for example, given any line segments, it is possible to construct an equilateral triangle on the line segments. How is this proven? Well, you take a line segment, a given line segment, you take this point as the center of a circle with this as its radius. And then you do the other thing, starting from this point. You draw a circle with that radius, with this as its center. And then you look at these two circles and they intersect. So another common notion is that you can mark off intersection points. Now, after you have this intersection point, you can, by the first axiom, given 2 points, extend a line segment between them. And between these 2 points, you can extend a line segment between them. Now, if you look at this segment here, it's the radius of this circle. Now, this point is on the boundary of the circle. It's on the boundary of both circles. That's precisely what defines the points. So this segment is also a radius. Therefore, this segment is equal to that segment by the definition of a circle. Similarly, this segment is equal to that segment by the definition of a circle. Now, by common notions, transitivity of equality, you have that those two segments, the blue ones, are in turn equal. Therefore, all 3 segments of this triangle are equal to one another. Therefore, you have constructed an equilateral triangle. So that's where the theory starts. Now, you can say a lot of interesting things about this argument. For example, how do you know that this intersection point exists? Now, Euclid doesn't address that, and I personally have lots of arguments for why he doesn't need to address that. You can also give modern objections which don't make full sense, such as, in Greek terms, such as, let's suppose that we were working with a plane in which only rational numbers exist, rational coordinates. Then if this is the unit length, this point right here would have irrational coordinates. So the point doesn't exist despite the fact that it looks like there should be an intersection point. Well, that argument wouldn't have made sense to the Greeks. So it doesn't really work as a valid objection to the theory. Again, under a very strict sense of what is a valid objection to a theory that I can't explain right now. Okay, so where does the theory go from there? You then get propositions like, let's suppose you have 2 parallel lines. So this is book 1. There are 13 books of Euclid, proposition 35. And that proposition says, for example, if I take a line segment here, and then I take 2 parallelograms that share this as their common base, and whose other sides are both based on this parallel line, and they're all equal, then the area of this parallelogram is equal to the area of this parallelogram. Of course, Euclid doesn't write area, he just writes that the parallelograms are equal. And then how does he prove this, for example? Well, look, this, by definition, this segment of a parallelogram is parallel to this segment of a parallelogram, right? And this segment of a parallelogram is parallel to this segment of a parallelogram. So let's put some letters here. Let's say A, B, C, D, E, F. Then look at triangle ACE. So it has vertex A, C, and E. And then also look at triangle B, D, F, which has vertex base here, then D and F. Now, if you look at it, these sides, CA and DB, are equal. Similarly, the sides AE and BF are equal. And you can also argue that these angles are equal. Therefore, these 2 triangles are equal, as in equal in area. I'm just sketching this argument. I'm not going over it in full detail. Then, given that these two triangles are equal, let's look at this triangle right here. This triangle right here is a common parts of these two triangles. Now, by the common notions, if you subtract an equal part from two equal things, the remainders are equal. So that establishes that this figure right here is equal to this figure right here. But then you go by another common notion, by applying the same common notion but for addition, look at this triangle right here. Well, if I add it to here, then I obtain this parallelogram. If I add it to here, then I obtain this parallelogram. These two are equal, and I've added something equal. Therefore, the wholes are equal. So that establishes that this parallelogram is equal to this parallelogram. Any questions about that? By the way, this isn't part of the course content, so you're definitely not going to need to know this beyond this lecture. But this is all in setup of a punchline that's delivered at the end, which sets the philosophical tone for this class. Any questions? Okay, I don't know what people think. Can anyone tell me what they think about what's currently going on? Do they understand it?
I can follow you.
Sorry, go ahead.
I'm following you.
Okay, good. Right, so what can you do from this theory from there? So then you get to book 2 of Euclid. And book 2, really, that is terrible handwriting. Carries arguments like this, translating things around. And the eventual arguments that it gets is, well, if you have anything called a rectilinear figure. So a rectilinear figure is an area in the plane that's bounded by line segments. So this is the area here is would be a rectilinear figure. It's an area, it's not the boundary. So what book 2 establishes is basically that if you take any rectilinear figure, you can cut it up into triangles. This is called for a triangulation. Another way that you can think about a rectilinear figure is that it is the area inside of a polygon. And book 2 shows that you can triangulate polygons. But that's not the final conclusion. Then if you look at any triangle, right, you can always take this triangle by the proposition in book 1, for example, and slide it along to any other position. So all of these triangles are equal, for example, if you slide it along the top vertex along a parallel line. And if you take any square and you draw a diagonal, then this part is equal to this part. And if you cut this side in half, well, if you take this triangle and you bisect this side here, then you get something of half the area. Or if you double the side, then you get something of double the area. So for every single triangle, you can show that you can convert it into a rectangle having the same base with equal area to a triangle. And then he also shows that for any rectangle, given any other base, you can construct a rectangle on that base, which is equal to that rectangle. And he also shows that you can construct a square equal to that given rectangle. So in other words, using triangles, we can replace triangles with equal area rectangles. Now we can take, for example, some unit length. So let's say we have all of these rectangles that are different. You can make all of these rectangles have a common base. So then you can stack them up one on top of the other and you get another rectangle. And then using the final proposition, you can convert that resulting rectangle of these stacked up rectangles into a square. So in other words, the final conclusion is that given any rectilinear figure, I can find a square with equal area. And that square is called the quadrature of the rectilinear figure. Now, what's an implication of the fact that you can find the quadrature? Well, let's say I have this rectilinear figure right here. And let's say I draw another rectilinear figure right here. And this figure has some area, this figure has some area. And I ask you which one of these two figures has the bigger area. Well, remember, we're working with compass and straight edge constructions here. So using only a compass and straight edge, you can construct squares with equal areas to these two figures. And then you can take those squares and you can put one square end to end with another square. And, well, either they'll align and it's an equal area, or one square will contain the other. So one area is bigger than another area. So using compass and straight edge, you can compare the areas of any two rectilinear figures. Does that make sense?
So they just like basically find as many rectangles and squares they can in a figure and then accumulate them all and then see which one's bigger, right?
Yes. And you don't need to know the details, but the process of accumulating them is first converting them all into rectangles, the triangles, into rectangles, then converting all of the rectangles to rectangles that share a common base so that you can stack them up, and then finally converting the resulting stack into a square.
Oh, okay. Interesting.
Right. So then remember this, the idea of Parmenides. Parmenides came and he said, well, you have a theory, you think you understand something, I can poke plenty of holes in it. So here's the idea of we want to talk about areas. I say that when I talk about areas, I know what I'm talking about. It makes sense to talk about areas. You won't find contradictions in my reasoning if I talk about areas. So really, the goal of all of this theory is to set up something where you can't have someone like Parmenides come in and show that there are a bunch of contradictions. Now, one thing that I want to mention is that in school, we're taught about numbers as lying on the number line. So this is like a modern notion, right? The Greeks did not have a number line. In fact, if you were sent back in time and you were taught how to speak Greek, and you tried to go to a Greek philosopher and convince them of why like real numbers exist or why a notion of a number line exists, they would laugh you out of the park and they'd be able to riddle your notion with holes. I guess arguably in the set theory notion section of this class, you'll learn how to make the notion of real numbers precise. But they require a lot of work. In fact, the point of this entire preface to the course is to show you how much work something like real numbers requires and how much subtlety there is involved. But just to give you an example of why you'd run into errors, so this is something that every single Greek philosopher would know. And I say philosopher because right now we have like distinctions between mathematicians, philosophers, astronomers. In the Greek world, you really didn't have distinctions like this. If you focused on only one area, by the predominant cultural ethos, that would be seen as terribly myopic. So everyone who is a philosopher, educated as a philosopher, including all mathematicians, they would know that you run into an issue with the following thing. Is a line made up of points? And is a square made up of lines? So yes or no? What do people think?
I would say yes.
So then I ask you the follow-up question of, well, what are the points that make up a line?
I mean, you can't really list them, but you can pick any one.
Right. So yeah, and then the Greek issue of that would be that you can't list them. You ask the question of, okay, well, if you're saying that you can take points and build a line, show me how you can do it, and then you can't because you can't list them, right? In some sense, you have the notion of like lengths and you have the notion of areas, and these are somehow categorically different things. You can't compare a length to an area, right? Sort of, you can think about it maybe as a dividing by zero issue. You can rephrase it in those terms. But right now, in modern terms, you can talk about the set of points on a line. That requires a lot of works, and the Greeks would have seen the issues in premature, not very rigorous ways of doing that. If you said that a line was made up of points, they could throw several things which would sound contradictory in the terms by which they meant made up out of. So, okay, that's, I guess, one issue. Well, so magnitudes then, areas, lengths, they don't represent some common notion of magnitudes. There was no single number that represented a length or a number that represented an equivalent area when thought of as an area. And you couldn't, Zeno, for example, has all of these arguments about motion, also Parmenides things. So things like dividing by zero and infinitely dividing something was something that they were very familiar with, and you run into a bunch of issues like that. Right, where was I going with this? Right, so they want to be very careful, and they don't want to run into Parmenides type issues. And if you start by saying things like a line is made up of points, then you really run into Parmenides type issues when you get to things that on a very high level can be described by dividing by zero. Or another different way is the fact that areas and lengths are uncomparable and areas and volumes are uncomparable. So that's a philosophical idea that's really there. And they're not unified in common into a number line. But in Euclid, you still have a theory about numbers. So, for example, if you have any magnitude, magnitude is either an area, length, or a volume, but if you just have any magnitude, you can arbitrarily call that magnitude a unit. And then they define numbers, and this is an interesting definition. A number is a multiplicity of units. So a number is any number of units. That sounds cyclic, but numbers are really serving two roles. There's numbers in the meta theory, which isn't something that's actually represented in geometry. You can talk about 2 units. You can make another unit. That's 2 units. That description of 2 units is something that we say in words, but in the actual theory, you have, well, the line segments on the page, right? So something like a number is a multiplicity of units isn't hopelessly cyclic, because there's this distinction between meta theory numbers and numbers in the actual theory, where a number in the actual theory, well, what is it? It's a multiplicity of units, right? So that's one thing that you can do. And this lets you talk about whole numbers. Well, specifically, it lets you talk about, let's say we don't include 0, Greeks, and it lets you talk about 1, 2, 3, 4, 5, not as abstract numbers, but as literal multiplicities of units. And then the Pythagoreans tried to construct from this a notion of ratios. And they basically constructed rational numbers. They had equivalents for ratios A over B. Now, there's an apocryphal story, meaning that it was definitely made up, 100% not true, that you take the unit, well, the math fact is true. You take a unit square, it's a square, its side lengths are 1, and you take its diagonal. Now, again, the Greeks did not have numbers. The square root of 2 was not a number. It doesn't make sense to talk about the square root of 2 in their theory. But you can talk about this diagonal. And you can talk about, do these two things have a ratio? In other words, if you take some multiple of this one, is it equal to some multiple of this one? And the Greeks saw that they weren't. Well, the Pythagoreans realized this because the Pythagoreans were the ones who constructed a theory of proportions that basically encompassed the rational numbers. So now the Polyphorcal story is that when the Greeks discovered the irrationality of the square root of 2, which is already wrong because the square root of 2 is a number and numbers didn't exist in their theory. But when they discovered this, the actual statement is the incommensurability of the diagonal of a unit square to its sides. Well, but when they discovered this, it was so shocking to their theory that they held it as a deeply hidden secret, and that when someone threatened to reveal the secret, they were thrown over a boat and drowned. And that person actually has a name, but that story is definitely not true. But no, the Pythagoreans didn't try and hide this fact. For the Pythagoreans, the way that they saw this is they wanted to have a theory of proportions, and their theory of proportions could not handle this proportion, which is sort of bad because you have this idea that there are areas and there are lengths, and all lengths are categorically the same type of length. You can, for example, see that the diagonal is bigger than the side, because if you just draw a circle and bring this over here, one segment is inside of the other, so you can compare them. But you can't form a proportion between them when you think only about rational numbers. So you have a theory of ratios, and that theory cannot account for this case. And it really looks like it should account for this case, because these two things look like they have a proportion because they're categorically the same type of magnitude. So that was one of the things that they ran into that is a problem. Let me just check the time. Okay. Now, the other thing that they ran into a problem is the following thing. You take a circle, right? So our theory of areas then, you sort of have confidence that when you have areas, you know what you're talking about. Why? Because you have this result. So this result predates Eudoxus, who's the main character of this story. And this result really tells you that areas make sense. If you have any two rectilinear figures, I can compare those two areas. That's something that substantiates the notion that you know what you're talking about makes sense. By the way, my window is broken, and I don't know if you can hear a dog barking, but I cannot close it. So that might be something that we have to deal with.
I don't hear anything.
Oh, good, thanks. Okay, that reassures me. Now, then, if you want your theory to be nice and wrapped up all in a bow, it would be nice then if you could take the quadrature of a circle. Because then if you had any circle and you had any rectilinear figure, if you could take the quadrature of a circle, you could compare whether the circle was bigger than any rectilinear figure, right? So that is a very desirable proposition. So people definitely wanted to find the quadrature of a circle because that would tie up their theory with a bow. It would provide a lot of credence to the idea of, you know what you're talking about when you talk about areas. You're not going to have someone like Parmenides come and shake the entire theory up. This really substantiates that areas are a notion that makes sense, which in a lot of ways of treating areas, it doesn't when you encounter division by zero errors. But no one could solve this problem. In fact, again, 19th century proof, it's impossible. No, 18th century proof, it's impossible to do. But Greeks could not see that it's impossible. They widely suspected that it was impossible at a certain point. It's not as though so many people were desperately trying to square the circle. Actually, that's a modern trend. There are a lot of crank mathematicians who say, I have a construction of this despite the proof that it's impossible. But this presented a bit of an issue. We talk about areas, and we say that a circle and a square both have areas, that the notion of area that applies to a circle, which is called a curvilinear figure, is the same notion of area that applies to a square. Now, why should they be the same? Well, because, for example, you can find a square contained in a circle, and then you can take the square and you can make copies of this square, and eventually you'll get something that exceeds the circle. Well, actually, that's a bit of a spoiler, but roughly anyone with 2 neurons can see that circles and squares have areas. The figures. I mean, this is something that's apparent to your intuition, right? But if you say that they're the same, then you encounter this issue of, well, you can't take the quadrature of a circle. So you can't compare an arbitrary curvilinear area to an arbitrary rectilinear area. And that doesn't make your theory be wrapped up in a bow. And then you begin to answer a question of, well, wait. Maybe the notions of areas of curvilinear and rectilinear figures are fundamentally different. What allows me to say that they're the same type of thing? And so here is the setup. You have a theory that's trying to be very careful to be something that in which you can't find a contradiction. And you're trying to extend this theory. And you get to 2 places. The first is that your theory has a theory of proportions, and it doesn't handle the case of a proportion of the diagonal of a unit square to its sides. In modern terms, we say the square root of 2 is irrational, but that's not how Greece spoke about it. And the other one is that you can't take a quadrature of a circle. And that brings into question your entire idea that area is like a thing that you understand and that you have access to, that it makes sense to talk about areas. Because you can't compare an area of a curvilinear figure to an area of a rectilinear figure. And these 2 problems became things that everyone would know about. For around 150 years ago, anyone who works on geometry would recognize, because of the sort of directedness of the Greek research program, that these 2 questions were the most important open problems in mathematics at the time. For 150 years. Everyone knows this. Then our protagonist of the story comes in. Eudoxus, in one paper, well, I say paper, but however it was disseminated, roughly 2 pages, solves both of these problems, resolves 150 years of open questions in mathematics, completely shakes up the world by storm. And the reason that he does this is because he has area. The concept, the abstract concept of area, Eudoxus owns it. He figures out philosophically what it means to talk about areas, and the concept becomes perfect. Now, I should mention the final thing. Along with these 2 open research problems, there was a final research problem that really related curvilinear and rectilinear areas together. And the comparability of them was captured in this hypothesis. Suppose I have 2 circles, and suppose they have diameters. Well, all circles have diameters. Then I can construct the squares on their diameters, literal squares. Oh, one more off-topic thing. You know, for example, the Pythagorean theorem, right? If you have a right triangle, then a squared plus b squared plus c squared is equal to 0. A squared plus b squared is equal to c squared. Now, what did the Greeks think about the Pythagorean theorem? They literally thought that if you take the square constructed on this side and the square constructed on this side, then those 2 squares together give you the square on this side. Multiplying 2 lengths doesn't give you a length. It gives you an area. Well, you didn't think of multiplication in the literal terms like that. So squaring meant literal forming squares on a side. Right. So suppose going back to this. You have 2 circles, you have 2 diameters. You form the squares on their diameters. Then the Greeks would like to say that, well, if I can form a proportion between them, so this really links both of the problems. Proportions don't look like they're something that works a lot of the time. So you want a theory of proportions, you want to extend the theory of proportions, and you want to link curvilinear and rectilinear areas. So this is a problem that combines both of those aspects. The problem is that two circles are to one another as the squares on their diameters. Now, in modern terms, which isn't how Greeks thought about it, let's say the circle has area C1, this circle has area C2, this diameter is D1, this diameter is D2. Then they said that C1 is to C2 as D1 squared is to D2 squared. Or in other words, C1 divided by C2, which is definitely not how Greeks thought about it, is equal to D1 squared divided by D2 squared. Now, why is this true in modern terms? Well, the area of a circle is pi r squared, right? So if you change the radius or you change the diameter, the area of a circle changes as the square of the factor by which you scale, right? So I know that, for example, in Calculus A here, they use a textbook, and the textbook, if you look at it at the beginning, it has a historical section about the prelude to calculus. And they say that Eudoxus proved a formula like A equals pi r squared, which is wrong on so many levels. Pi didn't exist as a number. There was no formula that gave an area of a circle. What Eudoxus proved was that two circles are to one another as the squares on their diameters. So that basically the most important research problem is this then. This research problem links these two questions, extending a theory of proportions and linking curvilinear areas to rectilinear areas. And Eudoxus solves this in a very quick argument, 2-page paper. And this, understanding this 2-page paper is basically a lesson of what it means to understand mathematics, what it means to have a concept of area. When you hear Eudoxus's argument, you're like, okay, damn, this person knows what area is. This person has a solid philosophical grasp on the notion of area. And you may say, well, like, why is it a thing that's, I can just talk about areas? Well, you're now going to see how much of a gap there is between the intuitive understanding of area exists, I can talk about areas, and a philosophically rigorous notion of here are areas, areas make sense. Okay, so here is where Eudoxus came in. Any questions leading up to Eudoxus's arguments?
I just have a question. So if Greeks didn't have the understanding of irrational numbers, then how did Pythagoras come up with the idea of like the golden mean? Because I know like the golden ratio is represented as 1.618, like it's an irrational number. So
right. You can, Eudoxian theory of proportions will let you construct proportions between magnitudes. Well, they'll let you construct ratios. Well, now, the Pythagoreans, for example, you can say that in modern terms, you would interpret them talking about the relationship of a diagonal of a square to a side of the square as talking about the number of square root 2, right? So for the golden ratio, I think that the statement is that if you take, so it is some rectangle such that this side has side length 1, this side has side length phi, and if you take the square here, then this is a square. That is a very bad square. If you take a square here, then this resulting thing is proportional to the original thing right here, right? So that defines this. The golden ratio is 1 plus the square root of 5 divided by 2. in modern terms. So that's description originally, that it's if you take a unit's length and then you construct a rectangle on this length, such that if you construct take the unit square away from it, the remainder is proportional to the original thing. That gives a description of this side. And then they can talk about this side in relation to this side, and that's like them talking about the golden ratio.
So they never expressed it as like a true number. They expressed it
not.
as like, huh?
They definitely did not. This is actually a very important thing about Greek mathematics. Greek mathematicians did not talk about real numbers. They did not talk about irrational numbers. They had whole numbers in the meta theory, but in the actual theory, there was no number line.
Got it. Okay.
And you're now going to see in Eudoxus' arguments why they didn't need a number line and why they could do things like calculus. Well, things that really look, oh, here's the single worst thing that ticks me off about the Math 125 textbook. They also say that by taking quadratures and other things, the Greeks were doing integration. Which,
yeah. Yeah, that seems like a big error on their part.
Yep.
I mean, I've had every math teacher I've ever had just like rip into how terrible the textbook is, but then they still use it, so.
Oh, I've been writing notes, and I'm never writing notes for another class again. No, writing notes takes way too long. It is, but yeah. There are some books are better than others, though. But I will be writing notes for this class. So, but I regret my choice already. Okay, so Eudoxian theory. Here we are. What does Eudoxus do? So first off, he solves this division by zero issue by saying what type of things will admit a ratio. We're only going to consider ratios of certain things. So if you, for example, say that I want to consider the ratio of a line to a point, you run into errors. Yeah, you can find a lot goes wrong with your theory if you say that you can do this. So one is, well, okay, I'll write the formal statements. Two magnitudes are said to have a ratio if multiples of one are capable of exceeding, if multiples of each are capable of exceeding the other. So what does this mean? This means, let's say I have one line segment and I have another line segments. Well, I can take the original line segments and I can consider multiples. Let's say this is the line that extends this. I can consider multiples of the original line segments, which just means I literally append copies of it end to end. Well, by appending multiple copies, I eventually get something that exceeds the other. Because if you have two lines with some length, some multiple of the first length eventually exceeds the other length, because both of them are lengths, and they're in the same world as lengths. Now, for example, if you take a circle and you take a square, well, I said it was a spoiler before. If you take the square and you just paste copies of the square end to end, you're eventually going to be able to cover the circle with finitely many squares, right? Just paste it. Like, imagine that you have a circle on a wall and it's a stain, and you want to cover up the stain with pieces of wallpaper, and the pieces of wallpaper have a given size. It's clear that you can use some number of pieces of wallpaper to cover up the stain because both are areas, right? And the other way around, you'd also paste circles to cover the square. Now they'd be intersecting, but anyway, this is some multiples of a circle. It is capable of exceeding a square. So these two things have a ratio. Now, what about a line segment and a square? Well, multiples of a line segment can't exceed a square. If you take some multiple of a line segment, you just get multiple line segments. And what would it mean to exceed? It would mean literally that you would have this last common notion, the part is greater than the whole. You have some whole that contains the part in a purely geometric sense. And so this theory prohibits things like this. Now, did the Greeks have a proof that the line and the square didn't have a ratio? I think they didn't. I think they would say that they wouldn't find this an important notion. Either way, answering the question of whether these two have a ratio or not isn't so important if your only goal is to avoid contradictions, avoid having someone like Parmenides come in. They know that if these two have a ratio, you're going to encounter some problems. But can you show that they have a ratio? Well, intuitively, it looks like you can't. And so unless someone finds a way to show that these two have a ratio, you're not going to admit them into your theory as having a ratio. And thus you're going to avoid division by zero problems, and thus you're safe. You're not going to have holes poked in your understanding. So this doesn't leave the room for finding holes, although it doesn't necessarily prove that holes can't be found. But that was secondary to having something in which you couldn't poke holes. Whoops. All right. So this is what we admit to have a ratio. To have a ratio. That looks bad. Here.
I'm sorry, but can you spell the name of the Greek that we're talking about?
The name of the mathematician?
Yes, please.
Yes. He is one of my favorite mathematicians.
Thank you.
And then as with all Greek names, it's Eudoxus of something. I don't remember what the of something is, but it specifies a unique name. Okay. And then, so this is what we have two ratios. And then the second definition is the definition of what a ratio is, or rather what it means for two ratios to be equal. So I won't write the definition yet. I'll say the second thing is something that says when two ratios are equal. Okay, before I give the definition, I'm going to give an example. So let's suppose that we have two ratios of numbers, and I'm going to denote the things as though they were actual. I'm going to denote the line segments as though they were numbers, which the Greeks didn't have, but it's useful for our modern understanding. So suppose you have A, some length, B as some other length, and then you have two other lengths, C, and you have D. Let's say it looks something like this. Okay, let's just look at A and B. Just looking at A and B. So as their lengths, you can put one copy of A inside B, and you can see, for example, here that B is bigger than A, right? I mean, this is an example. In this particular example, this line segment is shorter than that line segment, right? Okay, so this is a very beautiful picture. Imagine that this is a Greek column, and imagine that this is another Greek column. And imagine that these are also Greek columns. Now, look at the space between these Greek columns. And in a line extending outwards, add columns that are equally spaced. So this is an infinite line of spaced columns. So this is A, this is A, this is A, this is A. And similarly here, we're going to extend this, and we're going to put equally spaced columns. Okay, so this is the amazing part. So here we see that if we look at A and we look at B, we have B is bigger than A because of how we line them up. Now we can also look at, for example, 2 times A. I'll switch to blue. If we look at 2 times A, that's something that's bigger than B, just by looking here. Now, if we look at, for example, 2 times B, that's bigger than 2 times A. And if we look at 3 times A, then that's bigger than 2 times B, just because of how they're lined up. So in other words, for every single number, meaning whole numbers 0, 1, and 2, for every, and I'm going to write this in modern notation as actual numbers, n, comma, m, we can consider n copies of A and m copies of B. And lining them up end to end, we can ask whether this one is bigger than, less than, or equal to these. So for every single pair of numbers, these are 1, 2, 3 whole numbers, not including 0. We get a result of the comparison test. We get one of greater than, equals to, or less than. Now, here's the brilliant Eudoxus step. A ratio consists of the information of which one of these possibilities it is for every single number. So a ratio is this information. Now, if you want to say it precisely in Greek terms, well, translated by Heath, this is a complete mouthful. 2 ratios are equal. And let's say these are ratios of AB to CD. We call this the first, the 2 ratios are equal. The first to the second, and the second, the third to the fourth. So that's just if what? Well, so you choose a number n and you choose a number n, and then you multiply the first term of both ratios by that number. If equimultiples whatsoever, be taken. This, by the way, is a complete mouthful. The picture is there. Be taken of the first and the third. And equal multiples be taken of the second to the fourth, the second and fourth, then these equal multiples then these, let's say these, okay, I'll say it in words first and I'll write it down. Alike, so if equal multiples whatsoever be taken of the first and the third, and equal multiples whatsoever be taken of the second and the fourth, then the first multiple alike exceeds, is greater than or less than the second equal multiple. Okay, let's put this. Then the seconds, and then the first and seconds, and the third and fourth alike exceeds or greater, exceed or equal to or are less than. Okay, that's very badly worded. Okay, I will not write it down in the original wording. That is not the original wording. Then these alike exceed, fall short of, or equal. Specifically, this is my writing, a n times a vs n m times b has the same results as n times c versus m times d. So this is what a proportion is. A proportion is the information of when this happens with multiples. Now, you can, for example, form ratios of lengths and ratios of areas. It's impossible to compare. Okay, that wording, let's just ignore that very pretentious wording. You can take two lengths then, for example. And you can compare multiples of this length to multiples of this length, right? And then you can take two rectilinear areas. Now, if you take any multiple of this area and any multiple of that area, you can compare them because you can combine those figures. They are figures, and you can take the quadrature of multiples of this one and quadratures, the quadrature of multiples of that one. Therefore, you can actually find this information given any two rectilinear figures. Now, you can't compare multiples of the line segment to multiples of the square, but in this definition, you only have to compare multiples of the first and the second to the multiples of the second, and you only need to compare multiples of the third to multiples of the fourth. And then this alike, exceed, or equal to and equal multiples just means that the n that I use here is the same as the n that I use here, and the m that I use here is the same as the m that I use here. So I didn't say that as elegantly as I would have wanted to, but does anyone not understand this notion? I'd like you to ask me for clarification. Also, am I talking too quickly? Anyone, please?
I think it's going fine.
Okay, good. Now, then, how does Eudoxus prove this proposition? So this is the Eudoxian theory of proportions. This is when two things have a proportion, when multiples of each are capable of exceeding the other. And what is a proportion? A proportion is the information of when you take multiples of one and you take multiples of the other, whether they exceed or equal to or are less than. It is this information. And the picture that really explains it is this column picture. if you have two lengths, then what is their proportion? The proportion is this collection of information. So Amanda, I believe you asked me the question before of how did the Greeks then think about the golden ratio or the square root of 2? Well,
Yeah, I did.
Pythagoreans didn't have access to the Eudoxian theory, but eventually when the Eudoxian theory got put into place, what would they think of as the meaning of the proportion or the ratio of the square root of 2 to the unit length? It would mean precisely if you took multiples of the square root of 2 and you took multiples of the unit length, whether those multiples would exceed or fall short of the other.
Oh, so it's compared to like 1 unit length. Like if they
Yes.
had like a standard unit length, then that's what
Well, you can, they didn't, you arbitrarily set a standard unit length.
Yeah.
In particular, in this discussion of the square, just take any square, call a unit length the side of the square. Again, straight edge, not compass, so they can't measure it, but they can talk about two sides being equal. If we arbitrarily call this the units, then in modern terms, we'd call this the square root of 2. Concretely, don't forget about the numbers. It's just some length. This is the length of a side of a square, and this is the length of the diagonal of the square. But in modern terms, you could say maybe 1 in the square root of 2. And then you'd look at things like this. If you just took copies of the diagonal ends to ends, or you took copies of the side ends to ends, when do you get a bigger length here than here, right?
Mm-hmm.
So that's what the ratio is. That is how the Greeks thought about ratios. In other words, if you Greeks thought about numbers, sort of this is what the number meant to them. A number isn't a number on a number line. A number is a proportion. And what is a proportion? Well, it's certainly not an infinite decimal expansion of something. In modern terms, like real numbers are constructed by Dedekind cuts. It's not a Dedekind cut. It's not an infinite set or anything. It is the information, this collection of information. That's what a number is to them.
So they just like expressed it as simply variables, but they never defined what the variables equal to, right?
Yes. In other words, the variable represented not a number on the number line, but a magnitude, where magnitude fall in philosophically distinct categories. A magnitude of area is categorically different from a magnitude of length. Now, why is it categorically different? Well, Eudoxus tells you, because you're not capable of taking a multiple of one such that it exceeds the other.
Okay.
Right. Okay, and now let's get to Eudoxus's most beautiful discussion. And here comes the second point of this discussion. Parmenides was the first person to give, well, Parmenides used a lot of arguments by contradiction in his thing. He said, suppose we assume something. Well, then you get absurdity, so we have to reject the original thing. And now, people differ in modern day about how to interpret what Parmenides wrote. Popper, for example, thinks that Parmenides was fully serious in the sense that he was an astronomer and he saw in astronomy that trusting your senses got you to wrong places, and so he took that notion very seriously and he meant this in full earnestness. My history of maths professor at Cambridge, he had the opinion that when Parmenides wrote, he was deeply disdainful of the standard of arguments at the time. And his goal was to create a scientific crisis. His goal was to show that the standard of arguments at the time was inadequate and that the entire thing as a whole could be considered as finding a contradiction within the framework of reasoning that the Greeks had at the time. Right. So Eudoxus was the first mathematician that we have in record of using an argument by contradiction in mathematics. So the proposition is that two circles are to one another as the squares on their diameter. These two are found in Euclid, book 12, as propositions 1 and 2. Also I need to give a lemma, which is Euclid, book 10, proposition 1. So here's the lemma first. Eudoxus also proved this. And the lemma says that if you take any magnitude and you take any comparable magnitude means something such that these two have a ratio. Then if you take this magnitude and you remove from this magnitude more than half of the magnitude, and then from this magnitude in turn, you remove more than half of the magnitudes, then by doing this process, you will eventually get to a magnitude which is less than the other magnitude. So thinking about this in modern terms, in terms of numbers, let's say that we have a number like 10,000. And we have a number, actually too big, let's say 1,000. And we have a number like 7. Let's say we're only working with whole numbers. Can anyone tell me a number that's less than half of 1,000?
200.
Okay, tell me a number that's less than half of 200.
69.
Good choice. Okay, less than half of 69.
One.
Did you say 20?
Yeah.
Okay, next.
9.
Good, next.
4.
Yes, so at this point, you are eventually forced to find something that's less than 7. So this lemma said that, and the key hypothesis were that the two magnitudes were comparable. And if you think about what it means that they are comparable, it is that multiples of each are capable of exceeding the other. So given that you have that, you can see how roughly the Greeks would prove this proposition. Or in other words, you can also think about this as the claim that if you take any number, m, and let's say you divide it by 2 to the n, as the very, very much not what the Greeks did. Oh my God, so not what the Greeks did. Not the Greeks. If you take the limit as n goes to infinity of m divided by 2 to the n, it is 0. And 0 is less than any number epsilon, where epsilon is greater than 0. Okay, 0 is less than any, okay, 0 is less than any number that's not greater than 0, right? That's a bit of a tautology. So this is not how the Greeks thought about it. In modern day, you could, using calculus, reinterpret that as what the lemma is saying. But they're not talking about a limit. They're absolutely not talking about a limit. They're saying not when something gets close to 0, they're saying that if you take a specific number, for example, epsilon, then in a finite number of steps, this number will become less than epsilon. No limits, no infinite processes, no things tending to somewhere, just do this process. You will eventually get a number that's less than 0. You can do it at home. We just did it here, right? Okay, so that's the lemma. Okay, back to Eudoxus's proof, that Eudoxus's proof that two circles are to one another as the squares on their diameter. So this is Euclid's book 12, 1 and 2. The first proposition that he says is, suppose that we take two circles and the circles have diameters. So in our arguments, for our convenience, we'll call the circle C1, we'll call the circle C2, and we'll call this D1 and D2. So Eudoxus's lemma says that if you take any figure inscribed in the circle, let's say this, then on this circle, it makes sense to talk about inscribing a similar figure. And what Eudoxus shows is that if let's say A is inscribed in C1 and B is inscribed in C2, and A is similar to B, in other words, one is obtained by scaling the other. The ratios of the sides, the angles are the same, and the ratios of the sides are all equal. However, just talking about the angles being the same is enough to capture this notion. So what should the conclusion of the lemma be? The big lemma that we don't know how to do is that circles are to one another as the squares on their diameter, right? But we can do something that's sort of half of this by talking about not circles, but inscribed figures in the circles. So what should the conclusion of this lemma be? Anyone? Okay,
They
this
can
tells
be
me that I need to
compared?
better, go ahead.
That they can be compared.
Well, they're both areas, so they can be compared. But okay, so our goal is to show that the squares, that the circles are to one another as the squares on their diameters. I'll draw the squares on their diameter as well. Now, we don't know how to compare curvilinear areas to rectilinear areas, right? That's the big open question. But we do know how to compare rectilinear areas to rectilinear areas, right? So instead of talking about the circle, we talk about an inscribed shape in the circle, and then an inscribed shape in the circle here. So we'd like to show that, we would like to show C1 is to C2 as D1 squared is to D2 squared. Now, these are curvilinear areas, these are rectilinear areas. We can say something simpler if we're living in the worlds of rectilinear areas, then we can consider A over B, right? And so what should the lemma say?
Can you repeat the question?
Yeah. So let's suppose that I take two circles and they have diameters and I construct the squares on their diameters, right? I can consider the ratio of the squares on their diameters, right? And I can also inscribe in the circle any figure. Now, suppose I go to this other circle, which has a different shape, and I inscribe a figure in it such that these angles are equal to these angles. So roughly, this has the same shape, although it's a different size. Now, what can I say about the proportion of these two figures?
Wouldn't you say that like the length of the inscribed shape of one is proportional to the inscribed length of the other one? So they'll maintain the same
These are
proportion.
areas. You can take proportions of areas. Sorry, areas. So
So you can solve to see if they're proportional, right? Because you have an area of the two. So
yes. So they have a ratio. What do you claim about that ratio? That it's equal to the ratio of what?
Of the D1 squared over the D2 squared.
Exactly. So the ratio of these two is the ratio of rectilinear figures. We're still working in the world of mathematics that you could do before Eudoxus. I mean, apart from the fact that you're considering the ratio. And so it's a lemma that he does, but it's all classical. It doesn't have any really radical ideas that are different from him that say that, well, if I'm still living in rectilinear worlds, then, for example, if I make this circle twice as big, then the area of this inscribed figure becomes 4 times as big. Well, if I make the diameter twice as big, then the area of the inscribed figure becomes 4 times as big. So inscribed figures scale as the square on their diameters. And so you were right. The proportion of A to B, A is to B. We can also write A is to B as D1 squared is to D2 squared. Does anyone have any questions about this? So this is lemma. This is 10-1. Okay, here is Eudoxus's arguments. So this is the final punchline of this entire discussion. Eudoxus says, let's suppose we have any inscribed figure inside of a square. Well, I can take this side, I can take this point, I can form a rectangle that has this line flush with this side. Formally, I could take the midpoint of this, shoot a diagonal up, mark this point, extend a parallel line to here, and then extend perpendiculars here, and I get this rectangle. Now, take this point that's above the midpoint of the segments, and subdivide. Add this point to your figure and replace this original blue edge with these 2 green edges. Now, here's the thing. If you looked at the area of the circle in this figure, if you looked at this arc right here is smaller than the rectangle, because the rectangle contains this arc, right? Next, if you look at these segments right here, then this thing here is precisely half of the area of the blue rectangle. So in other words, from the original area of this arc, I'm subtracting something and the thing that I'm subtracting is half of the area of something that's bigger than this. In other words, if I look at the area that is in between the inscribed figure and the circle, then by subdividing, I reduce the leftover area by more than half. So by the lemma 10-1, if I take any other area, let's say if C is any other area, then the difference from the square and the circle in areas is also an area. And by repeatedly subdividing, I can make that difference be smaller than the area C. By C being an area, it is comparable, and therefore this lemma about eventually having a leftover be less than any other comparable magnitude, that's called the exhaustion lemma. And so this argument says that, for example, inscribed polygons as the Greeks would say, exhausts the circle. The area left over from the circle and the polygons, in calculus terms, not in Greek terms, goes to 0. But in Greek terms, they would think about it as, given any other area, you can eventually make the leftover be smaller than that given area. So that's where the exhaustion lemma applies. Now, here's a bit of a questionable thing. Okay, so Eudoxus says this. Eudoxus says, suppose C1, if you look at C1, if you look at the ratio of D1 squared to D2 squared, suppose that it is not the same ratio as C1 to C2. Then, okay, this is something that you have to take on faith. There is some area, let's call it G. Let's call it alpha. Let's call it alpha. Then there is some area such that C1 is to alpha as D1 squared is to D2 squared, and alpha does not equal to C1. So C1 is to some area that is, C2 is not equal to C2, is the thing that gives you equalities of proportion is something that's characteristically different. It's an area, so in other words, we can consider the difference between alpha and C2. Now suppose that alpha is less than C2. So in other words, if you look at your original circle, then the ratio of this, the squares on their diameters, they have ratios. Oh no, there is drilling outside. This square has ratio to this square as this circle has to an area that's smaller than this. But because they're both areas, the difference is also an area. Well, it's not necessarily a circle and you can't necessarily put it inside, but it is something that's comparable to this. Then you basically consider the difference then C2 minus alpha, and by virtue of what this difference is, you eventually show that if you can inscribe polygons here, these polygons eventually they are eventually arbitrarily close to this area. Similar polygons here, which have the same ratio, are eventually arbitrarily close to this area. But in light of what this information is, the difference C2 minus alpha, you can carry this over and you can do a bit of algebra and you get a contradiction, because you eventually get that the area of some inscribed polygon here has to be bigger than alpha. So you eventually get alpha is less than some inscribed, well, no. You eventually get that all of the inscribed polygons are less than alpha is less than C2, but there's a difference here, and the fact that you can exceed it gives to a contradiction. So the precise way to do the algebra, I'm not going to show you, but the idea should sort of fall out from here. You start with this idea that, well, if rectangles have this proportion, and then you have the idea that, I'm going to switch to a different microphone. Do people hear sawing noises outside of my window now? Well, a while ago. Okay, can you hear me? Let's do this. Okay, can you hear me now? So
Yeah.
So this drives a contradiction. And then he supposes the other thing. Actually, he does not suppose that, he doesn't do the case C2 is greater than alpha. Instead of reproving everything that he did before, he does something clever, and he shows that the other case reduces to this case. So he does a reduction. But he shows that both assumptions, that alpha is bigger than C2 and that alpha is less than C2, lead to a contradiction, where the contradiction critically uses this exhaustion lemma. And therefore, two circles are to one another as the squares on their diameter, because assuming that they're not to one another as the squares on their diameter, then you say, well, then the first circle is to something that's different from the second circle as the squares on the diameter are to each other. Then it's either bigger or it's less than, because it's an area. And by looking at the difference and by applying the exhaustion lemma, you get to a contradiction. So it can't be that the area is C2 is bigger than alpha is bigger than C2, or alpha is less than C2. So alpha is equal to C2. Now this construction is non-constructive. You get to a contradiction. And by a contradiction implies this. And this is the first argument in mathematics that survives that uses contradiction. So this is the birth of Parmenides' idea of contradiction inserted into mathematics. It also shows philosophically how you can make a theory of area. Area, you get all of these issues of division by zero, but here you've avoided all of them by saying what two things have an area. And you avoid talking about a real number line or other things by capturing a notion of numbers. What are numbers? Numbers are the information of these comparison tests. So that thing alone gives you a theory that is strong enough to prove that two circles are to one another as the squares on their diameter. That also answers the question of comparability of curvilinear areas and rectilinear areas. Actually, in fact, here's the way Greeks would not think about it like this. But suppose I have an arbitrary rectilinear area on the page, and that I have an arbitrary curvilinear area on the page. Then, in fact, if I look at circumscribed polygons, and I also consider ways to subdivide the circumscribed polygons, where you subdivide it like this, then you can show, you'd subdivide it like this, tangent to this, with the halfway points. Then eventually this area also cuts down. So you can do this both from outside and from inside. Well, the circumscribed and the inscribed things, they're rectilinear areas. So you can do the following process. You can start with some inscribed polygon, and you can start with some circumscribed polygon, and then you can compare the circumscribed polygon, the inscribed polygon, and the unknown curvilinear area, right? So you have some unknown area of the circle, let's call it C. And then let's say you have terms, inscribed things, let's call them A sub n. These are all less than the circle, and then you have the circumscribed things, which are all bigger than the circle. You can't compare the circle to this area, but you can compare A sub n, and you can compare B sub n to this area. Now let's call this area D. If you eventually have that D is less than A sub n is less than B sub n, then the area of D is less than the area of the circle, because there is some inscribed polygon in there that's a part of it that you can compare and get something bigger than this, because you can take its quadrature and the squares are contained in another. On the other hand, if you eventually have that D is greater than B sub n, which are all of these things which are bigger than the circle, then you have that the D is bigger than the circle. Oh, I said it the other, no, then you eventually have that D is bigger than the circle, right, exactly. Now, so you do step by step, you take repeated approximations. Now, unless the circle is equal area to the square, this argument shows that eventually you'll have one of these to occur. So it's also possible to compare curvilinear areas to rectilinear areas, but you wouldn't know if you had equality, because this process would never stop. But when would you have equality?
Suppose that all of your constructions were made not from arbitrary circles and squares, but starting with some unit length. Well, if the circle is related to that unit length and the square is, then you would only have equality precisely when you construct a square with equal area to a circle. So then you, in order to have this process not always yield a result, you will have had to find some way in your theory to find the quadrature of a circle, which cyclically prevents the need of the original problem in the first place. So this is so logically tight, it just coincidentally works out like this. So this is what it means to understand area. This is why you don't need real numbers if you're doing it like the Greeks did it. This is why Newton didn't do calculus in the Principia. And this is what it means to have a rigorously hard constructed philosophical theory that accounts for areas. Oh, wow, okay, that was longer. So I haven't started the content of the course yet. So that was my preamble lecture. Now, where does this lead into the course? So there are several points. To understand mathematics, there are a lot of subtle points. And you can easily run into problems if you don't recognize what those subtle points are. Now, the fact that we have a theory that does mathematics and that has numbers took centuries of innovation. For example, the way, in order for Eudoxus to get his theory of ratios, he had to solve 150 years of the most important open problems of mathematics, which he did in this single paper. Now, it took centuries to get to the notion of real numbers, and the things involved there are far, far, far more subtle than Eudoxus's arguments. But now, if you want numbers, you have to have in mind, well, the people who developed this had to have in mind all of the issues that the Greeks ran into, how the Greeks came about those issues, and you had to do something that would even exceed that, that would let you talk about numbers on a number line that avoided all of the philosophical issues that the Greeks tried to avoid, and that had all of this technology. And that is an incredibly subtle construction. So this should hopefully give you an idea that, yes, having rigorous, well-founded theory of mathematics is a substantial thing that can be an open problem for many years. Now, when it already exists, you don't actually need to worry about those subtleties. Let me plug this one thing in. Right, here we are. Also, okay, so what are the other points? The other points are the structure of Greek society with this idea of a research program, and this idea that, well, why would you care about compass and straight edge constructions? Because if you're in the Greek research program and you have a notion of area that's founded on compass and straight edge constructions, then the idea of being able to trisect an angle under the restrictions of compass and straight edge constructions is something that you deeply care about, because you already have all of mathematics founded in the framework of compass and straight edge constructions. Therefore, saying something new about compass and straight edge constructions like trisection of angles says something new about the rest of existing mathematics at that point in time. If you're outside of this framework, you don't care about those constraints because those constraints seem arbitrary. You're not invested in those constraints. So being in the research program and being invested in the problems is actually necessary. Well, being invested in the methods is necessary to even care about the major open problems. They only make sense if you're already in this framework and you already understand mathematics. So the language of mathematics, in a way, dictates what the problems are. They open avenues for you to actually care about new problems. That's another thing that we get from this discussion. And then also the fact that this argument went by contradiction, which is an idea that we'll explore later. So that's the conclusion of this entire Greek section. That took way longer than I expected. Now I'm actually going to start the content in earnest. But any questions about this? Okay, so that was a bit more rambly than I expected, and I initially wanted to have slides for this, but slides weren't working. But you have not notes for this, but notes for what I was going to cover today. By the way, let's take a let's break until 3:55, 7-minute break, since I've been talking for so long. Everyone's good with that? So we're going to resume at 3:55. And anyone can ask me questions in the meanwhile. Also, none of this is part of the main course contents, but it should set a few things up. And the example with the sun and the moon should have set up a few things about problem solving and thinking logically, which are also themes, which I will talk about after I get through some of the actual main course contents, which will start then. Okay, I'll be back in a minute. Okay, does everyone hear me?
Yes.
Okay, now, so let's actually start with the course contents proper. I promise this is going to be more concrete, but not necessarily with this lecture. Specifically, when I was in first year, this is the exact thing that I was introduced to, what I'm about to describe, in the first week of lectures in my introductory CS class. Now, the example there, it was beautiful, it was understandable, and I want to explain exactly the same thing. But when I try and write it out and when I try and explain it, I'm really tempted to insert a bunch of things which basically outline everything that we're going to see in the first half of this class. Now, the ideas seem very abstract and not grounded, but that's because we really have half of the semester to sort this out. I'm going to keep talking about the same ideas over and over again. The first half of the class is going to be this class where we talk about syntax. That's the main notion, syntax. And I really hope to have slides for this, but a few things weren't working. And we're going to talk about formal systems. Now, to this end, we're also going to do a bit of programming in the programming language Rackets. Now, Racket is a dialect of Scheme, and Scheme is in turn a family of dialects of Lisp. And this is a programming language which I don't expect anyone to be familiar with, nor do I expect anyone to be familiar with programming. But if you don't know programming, all the better, because if you do know programming, you're probably going to have to unlearn a lot of what you know when looking at this language. It is the second oldest programming language that survives, Lisp specifically, and Racket is very similar to the original instance of the language. The language was also the first language such that the code of the language, the code was an object in the language. It was a language that could modify its own code. And you could also think about what a program was doing in very elementary terms, as though programs were being run on a page, as though you were doing algebra on a page. You can understand this programming language without reference to computers. You can understand its behavior as a sentence on a piece of paper rewriting itself by following directions. Where you can think of a sentence on a piece of paper as some sort of arithmetic expression. So if I say, for example, 3 times 2 plus 1 times 7, you may say, whoops, 1 times 7. I may ask you, well, let's evaluate this. And then you could write on the page, well, I'm going to rewrite 3 times 2 as 6. And I'm going to leave 1 plus 7. Let's do it one step at a time. And then I'm going to rewrite 1 plus 7 as 7. And I'm going to take 6 and 7, and I'm going to add them, and I'm going to get 13. And programs in Lisp will basically function exactly like this example. The way that a program will evolve is that at each step, the program is going to simplify itself until it eventually gets down to an answer. So if you're unfamiliar with programming, this is definitely the best language to start with. And it's also a paradigm that's much nicer to learn if you don't know another programming language. For example, this language does not have variables that you can change. It does not have loops. You have to write everything recursively. Now, if you do know programming, not having loops and not having rewritable variables, not having state removes all of the things that you're used to. So that's all is something that I want to say for people who are worried about the fact that we're going to be using a programming language. Oh, there's a question. What is the coolest language in the world? Typed functional programming languages. Oh, so Lisp is an example of a functional programming language. Now, the coolest functional programming languages are functional programming languages that also have types, which is actually what the second half of the course is about, which is the logic part of the class. So this is part one. All of this, in a certain sense, is in service to talking about logic and talking about putting logic on a computer. You can think of, in a sense, the way that a computer sees a proof as similar to the way that a typed functional programming language sees statements about type safety of its functions. That's a very abstract statement, which you're definitely not expected to understand right now, but eventually we'll get there. But there are languages that basically, before you compile them, prove theorems about themselves. You can think of maybe Agda or Haskell or Coq as languages like this, COQ. Now, in the course of looking at part one, we'll encounter a lot of proofs when we discuss proving things about formal systems. And that'll get us in the spirit of writing arguments, but all of those arguments are arguments that I'm going to call informal arguments. The standard of an informal argument is that it's an argument that I accept when you submit it for homework, or it convinces someone. You're necessarily, as we're going to see at the end when we look at formal arguments, going to cut a lot of logical corners, but they're going to be like acceptable uses, acceptable shortcuts. And you're going to see the difference between an informal proof and a formal proof very clearly, because this class involves both writing informal proofs and then moving to formal proofs. Now, the usual content of Math 250 is supposed to be an introduction to the language of mathematics. And that in part involves set theory. And I need to ensure that you know this, because my goal in this class is to teach you something that will serve as a core to any further studies in mathematics and computer science. I want you to start thinking in math and thinking in abstractions that are relevant to both mathematics and computer science. Now, everyone has to go through this process of sort of rewiring their brain to work in abstract terms. I went through this. Everyone who does math and CS had to go through it at some certain point in time. And I, while teaching this class, intend to discover a lot about how to get people through that process. As such, there's going to be a lot of debugging that I'm going to have to do. And I might be saying things which aren't effective to you. And if they're not effective, please interrupt me and please ask questions. So the first part of this class, what we had before, that was just sort of setting the stage philosophically. From now on, this is the main content of the class, and it's very important to me that you're not lost. It's also, so if you're lost in lecture, it's very likely that everyone else is lost in lecture as well. Please, it's much easier for me if you just interrupt me and tell me what's unclear. And you should also reach out for me for office hours, which I can schedule anytime. I love to talk, as you can probably see. I'd be willing to sit down with you for half an hour to an hour and explain everything that you need to understand. So that's going to be explained. Next off, this class, the goal is to teach you how to solve problems in abstractions. As such, there's going to be a very large component of solving problems. Some of these problems are going to be coding problems. The problems are going to be ones where there are some unique twists to the problem where you would not have seen how to solve this problem exactly before. The entire point of the problem is to teach you about how to come up with a solution to a problem. That's one of the primary meta goals of this class. As such, When you encounter something and you don't know how to solve it, you're inevitably, I also inevitably, always frustrated when I don't do this. You have to sit through a bunch of frustration, and then you also begin to feel a lot of insecurity. You feel that other people get to this thing quicker than you do. And then you start to worry about this, and it starts to cause stress. I definitely experience a large amount of this, but you have to get through this. That's a very important skill to learn. All of this is going to seem intimidating at first, but there's a very real thing about persevering through the intimidation and just sticking with something stubbornly enough for a very long time until you finally get it. Most of math is sitting and being very frustrated. And then like 0.5% of the time, you actually understand something. And then you go from I'm a complete idiot to, oh my God, I am a genius. A very, very, very short period of time, but somehow this makes it worth it for a lot of people. Right, so you're going to be frustrated. You're not going to know what's going on. Now, this might be because either I really assigned a problem that's inappropriate, which hopefully I should fix if enough people tell me about that, or it's something which is an actual challenge. We can set up times, but being stuck and getting unstuck are very important parts of doing mathematics. Right, so I got into that tangent while also talking about set theory. Set theory is the main core of this class. Well, it is not the main core of this class. It is the main core of standard offerings of this class. And this is going to be desynchronous. Now, I said that you'd have to do something by Wednesday, but I don't have my set theory notes ready yet. And I went way too long for the first part, so I'm not going to cover all of the content that I had prepared for this lecture. So set theory, you're going to have to read the first thing by later. I'll tell you when, soon. But I'll record lectures, and I already have like 10 pages of notes for that. I also have lecture notes for this, which I sent you. They're actually very meticulous. They look much nicer than me handwriting. It's because I couldn't get slides to work, because there are 3 programming languages that I'm working with in order to get slides to work in this cumulative environment. Right. So going back to this, as with this, there are going to be lecture notes. Oops. And videos. Now, why are we doing set theory? Why is it important that you go through this material? And you definitely have to go through this material. Actually, as an instructor, the department expects of me as my primary role to ensure that you know this content. In a certain sense, I have to police that you do know the content of the third part of the class. With a lot of the other things, we're going to be talking about things at a slightly abstract level. It's not 100% necessary that you understand everything that's said, so long as you get the main idea, and then you can refine your understanding. This is going to be material where there are a lot of different levels of refinement that you can apply. Oh, okay, so I am going to post the notes and the videos. The videos right now, by default, are available on Blackboard automatically when they're recorded. I also intend to edit these videos, make them slightly presentable, and that I can post them to the people who are auditing the class. But as for the notes, there's going to be a link on the course webpage, and everyone should have received an email with a copy to the main notes already. And the set theory notes I haven't put up yet, but I want to rewrite how I write a few sections. Now, okay, so why is set theory important? Why does the department say this? It's because in a certain sense, set theory is the de facto language of mathematics. If you look at any piece of modern mathematics, almost any, and you look at how it's written, they don't necessarily explicitly talk about sets, but there's a lot of implicit uses about sets. The philosophical effect of set theory has a lot of repercussions about the way that mathematics is written. And if you're not literate in the language of math, then sometimes a lot of math becomes unclear. And so if you want to read most of mathematics, and if you want to understand most of mathematics, you have to know a bit about set theory. Now, set theory is not, as a foundational theory, something that's somehow indispensable. It is a foundation in the same way that Eudoxus had a foundation, but we don't think about the Eudoxian foundation when we think about numbers. So set theory sometimes is a bit weird, and it's weird in the ways that it is, but its weirdnesses permeate in mathematics. If we replace set theory with a different foundation, such as one on type theory, which is what we're going to be covering in the second part of the class, then mathematics would look different. In fact, proof assistants are based on a foundation that's different from set theory. But nonetheless, you have to know some foundation. This is the predominant one. If you want to understand math, you have to see it. It's also a very good example of what a mathematical theory looks like. So I'll send you information about those notes at that time. So that's an outline of what we're covering in the class. Now, in this first lecture, we're going to look at getting to proofs. Oh, right. So as for proof writing, which is also, this class is supposed to teach you how to write proofs. There are three different ways in which this class will teach you to write proofs, corresponding to each one of these portions. Set theory will teach you how to write proofs interacting with the common language of math. So the common language of math talks about certain things, and you will now know how to work with those certain things because they're sets, and this teaches you how to work with sets. Next off, we're going to look at informal proofs that make sense to you when discussing formal systems and proving properties about formal systems. What are a formal system? Well, I'll give you an example this lecture. Then after going through all of this formal system stuff and writing all of these informal arguments, we're going to have an idea, well, this is maybe what a proof looks like. Well, what principles did I use to do this proof? What are the ideas that go into a proof? How can I make a computer understand a proof? And I personally think that this question of how do I put something on a computer is perhaps one of the most fruitful questions in mathematics. You really understand something if you can make a computer understand that thing. And we're going to see, with the goal of putting logic on a computer and being able to write math arguments on a computer, your principles of what a proof is are going to come out very strongly, and they're going to recontextualize all of the informal proofs that we had done up to that point. So formal proof is a very different beast from informal proof, and you have to go through the informal proofs first. Now, the way that this course is set up, the informal proofs also teach you everything that you need to know about computers and about proofs, so that we can combine those two goals and put proofs on a computer. Right. So this is the outline. Any questions about that? Okay, I have half an hour. These lectures generally won't take this long. I'll spend less time, but the first parts took really, really much longer. So let's just start with the main content of the class. Okay, the first thing that we're going to discuss is numbers. Now, in this class, by number, I mean natural number. So we're not actually going to use any different types of number in this class, really. Now, what is a natural number? Well, what's one definition of a natural number? Well, a natural number, this is any of 0, 1, 2, 3, and so on. Now, what does that mean? 1, 2, 3, and so on. Well, it may be a bit vague, but from this, you can probably see that, for example, -17, negative numbers, and fractional numbers are not numbers. Or, well, they're not natural numbers. But when I say number, I always mean natural number, right? So what I've said right now, that the natural numbers are any of 0, 1, 2, 3, ... and -17 and 1/2 are not natural numbers, might tell you what I mean, right? Is anyone not clear what I mean by natural number? On a very surface level. So for example, 57 is a natural number, right? Now, so our goal is really also to understand what math is all about. In understanding what math is all about, let's go back to the first types of math that we learned about numbers. So all the way back to preschool. We're not going to talk about fractions. We're not going to talk about negative numbers. We're not even going to talk about multiplication. Let's just talk about numbers, counting, and addition in the way that we talked about them in preschool, in kindergarten. So in kindergarten, they did not define a natural number in this way. This is most certainly not how you defined numbers. Natural numbers are any of 0, 1, 2, 3. -17 and 1/2 are not numbers. That's not how it was explained in kindergarten. So I actually looked up, I'm Canadian, I'm currently in Canada, and I looked up what the kindergarten guides are, and I looked up how they explain numbers to children. So I can confirm that this is what happens. So how, this is a question I'm asking you, how in kindergarten do you introduce the question of numbers? What does anyone think?
Well, they use objects.
Oh, good, so go on.
For instance, they'll give the child a box with marbles. And first, there are no marbles on the table. And then the child can take out one. And you have, so that would be 1. Then you can take out 2. So you have 2. You take out 3. Then you have 3, and so on.
Very good. Oh, actually, if I remember correctly, you're in the education program, right? By your name. Okay, so we actually have someone who is an expert on pedagogy here. So yes, exactly. Then here's a kindergarten definition of numbers. A number is an answer to a question of the form, how many apples are there in a basket? Is that a good answer, do you think? So how in preschool they describe numbers, the way that I said it. Answers are the definite answers to the question, how many apples are there in a basket? I guess not a basket, but this basket. Now, how would children learn? Let's see the chats. Yes, okay, good. So yeah, right, there was a clarification. Positive integers or positive integers including 0. Yeah, so 0 is included. However, also it's an interesting point. The word positive doesn't have a very strict meaning. I went to a PhD interview, well, I guess an open house at Toronto, and I really wanted to talk to this eccentric mathematician called George Eliot, and I knew a lot of the reasons that he was eccentric. And I answered one of his questions. He told me to come to a lecture, which started half an hour late. And then I answered positive to mean greater than 0. And then he said, no, you're wrong. And I said, no, I meant this. And then he actually gave me a 15-minute talk as to why positive should include 0. So you can make arguments about this. Anyway, okay, completely going off topic. So in kindergarten, you ask a child how many apples are there in a basket. How do you know how many apples there are in a basket?
You count
You have
them.
to take them all out.
Yes, very, very good. So there is this actual notion of counting. You start by removing apples from the basket. You start with 0, then you remove 1, then you add 1, then you remove another, and then you add another. So you count up to the number of apples that there are in a basket, right? So if numbers are the answers to questions of the form, how many apples there are in a basket, and you answer the question of how many apples there are in a basket by counting, and also if numbers are exactly the answers to this question, in other words, for every number, you can imagine a basket with that many apples. Let's ignore questions about the fact that you can't fit 1 million apples in a basket. That's sort of boring. Let's say all numbers are like this. Then what does that say? That says that for any number, you can count up to that number starting with 0, right? Okay, then so that's an interesting notion. Well, then we also learn about addition. And I now want to think about addition in preschool terms, not in first grade terms. In preschool terms, what does it mean to add two numbers?
So if you add a natural number A and natural number B, you count to A and then you count how many numbers you add to get to B, and then you put the number of the numbers to count together.
Oh, so well, let's say it like, well, how do you put them together? So let's say you actually have two baskets in front of you, right?
Okay, use an example like 4 and 6.
Yeah, so you have a basket of 4 apples and a basket of 6 apples in front of you.
Okay, let's say that you write one line as 0, 1, 2, 3, 4. Another line is 0, 1, 2, 3, 4, 5, 6.
Yep.
And then you change the 0 at the second line to be 5, change the 1 to 7, change the 2 to 8, and so on until they reach the end.
Oh, really good. So what you're saying then is that we count one basket and then we start counting the other basket, but instead of starting at 0, we start at the result that we had before, right?
Well, the number after the result.
Oh,
Yeah.
well, oh, I mean, instead of starting at 0, you start at, so like, let's say 5 plus 3, right?
Yeah.
So if thinking of 5 as a count, you can think of 5 as being 0 plus 1 plus 1. By the way, so your answer is right. Like, yeah, that's exactly the point. So 5 looks like this. Well, there are no equalities, no addition. We're trying to define addition, but 5 is just something that you count up to 5 from 0. If we'd represent it like this, they wouldn't represent it like this in kindergarten. And then 3 looks like this.
Yeah.
Now, you count the 5 baskets, and then instead of counting the 3 baskets in the way that you usually would, you consider 5. And then you start You take this number and then you start counting up, right?
Yes.
So as for our education major, is that good?
It looks good, but your first parentheses have 1, 2, 3, 4, 5, 6 ones there.
Oh, okay. Being a mathematician may actually result in your skill of counting being lower than usual. We don't do calculations. In MIT, I know that the tradition is that when your group is eating at a restaurant, the person who calculates the check is the youngest person who's not a math major. Right, okay. But the philosophical idea of this is how you present it, does that sound good? So like, this is how you add in kindergarten, right?
Yes.
Yeah, so it actually makes you think. The addition is in first grade. Now, in first grade, you learn something different. In first grade, you actually think of numbers as decimals, and you learn about addition in column form, like 15 plus, let's say, 16. You get 1, you carry the 1, you get 3. That's not how you're taught it in kindergarten. In kindergarten, it's just this. This is addition. You count 1, and then you count the others. Well, you start counting from that 1, and then you count the other. Then you have an idea like, well, if I count one basket first and then I count another basket, or I do it the other way around, I'm going to get the same results. Can anyone think of a really good argument as to why those two are the same? Kindergarten level argument. So in other words, the question is, why is 5 plus 3 the same thing as 3 plus 5 at this level of discussion?
Because you're always, yeah.
Because, sorry?
You can go.
I didn't hear that.
Oh, I think because you can switch them around, it doesn't make a difference. The baskets.
Oh, okay. So the thing that I had in mind is, well, there are like various different ones, but you'd get the same thing as had you dumped all the apples in the third basket. So that's one. But there's also, even before all of this, you don't need to do arguments like this. Sort of in our brains, it's built in the idea that if we shuffle around apples, we're not going to change the number of apples just by shuffling around. So for example, if you go to a child and then you show them some number of objects and then you shuffle them around, and they're not just objects, they're pieces of candy. So the child's really invested. And so you show them candy, you shuffle it around, suddenly there are fewer pieces of candy than before. Then the child knows that something's up, they're upset because they want the candy, and then suddenly there's less candy. In fact, looking at cognitive development literature, this idea of object permanence is something that's usually developed like in a very strong way between 8 and 12 months. So somehow in our biology, the notion of shuffling things around doesn't change their number is really hardwired. And so the idea that counting one or the other way around doesn't change it is intuitively obvious because our biology makes it that way.
I think in like educational theory, my dad was telling me that most children learn ostensively, where you have to point to an object and then say what the name is for a child to understand it, because they don't understand like verbal definitions.
Yes.
So usually
Ostensible. Go ahead.
So you have to point to something and then say what the name is, like door. And then the child will start to develop the association between like the number or like the name and the object, or the number and the object.
Exactly. So for example, a very good philosopher of language is Wittgenstein, sort of causing this entire linguistic twist. And then Wittgenstein talks about ostensive definitions a lot, and then ostensive definitions are just definitions by pointing. That's the common thing. So yeah, exactly. So that's how you teach children how an apple is. And in a certain sense, there are going to be some ostensible definitions in this lecture because I need to get some concepts across, but we're eventually going to intuitively understand them. So, okay, so this is a bit of a preamble. So we have this idea that, okay, this property, which is called commutativity of addition, when we talk about addition in this way, it really relies on our notion of object permanence. But the fact that it's obvious is a bit of a problem, because when you ask why, you say, well, it's obvious. Well, why is it obvious? Why? What's the deeper reason? And then if you're relying on this model, it's hard to give, well, you can give a bunch of things, but they're sort of going to be informal and intuitive. So how can we see a property like this more carefully? Or putting it in another way, if we rely on intuitive properties about numbers, then you also have properties about numbers that really aren't intuitive, like Fermat's last theorem, the problem of like the Pythagorean equation, but with an exponent of n that's different from 1, finding solutions where a, b, and c are non-zero. It is impossible to find any integer solutions with no zeros for n is greater than 3 for any 3. This is a very famous problem that was solved by Andrew Wiles in 1995, but this is an example of an incredibly non-obvious property about numbers. And it's not obvious. It's definitely not obvious. It is the furthest thing from obvious as far as statements about the numbers go. So if we want to eventually get to, obviously not in this class, understanding properties about the numbers, in this class we're going to look at less sophisticated ones than this. How do we see it when it's not intuitive? Right. And so for this, you might want a different model of the natural numbers, a more formal, a more logical model of the numbers. And maybe in this formal model, it's not going to be obvious why commutativity addition holds. It's not going to be clear, and then you're going to fight for it, and you're going to find a reason. And that reason is going to be something substantial. It's going to tell you something about arguing. It's going to tell you something about numbers. So that's a cool thing. So let's see, what is our model of the natural numbers, where the motivation of why we would want a model of the natural numbers is to solve the problem of something being obvious. We don't like it when something's obvious. It's a false comfort in a way, as far as finding non-obvious properties about the numbers. So that's our motivation. That's the motivation going in. Now, right, so in first grade, in first grade, you actually learn about numbers as being numerals. So for example, you have 37. 37 defines a number, and you learn about addition in a different way than you did in kindergarten. You learn about column addition, as I gave you an example before. So that's a different notion of addition than this one. And numerals, in a certain way, you can construct them. And they have rules about the way you can construct them. Sometimes we'll say that, well, 0 is a numeral, but you shouldn't have non-zero numbers being denoted by numerals with leading zeros. For example, 007. This is a convention, but you can say by convention, this should actually be written as 7. If we're talking about numbers, so again, whole numbers, 0, 1, 2, 3, also non-negative, the natural numbers, then the convention of not having leading zeros in non-zero numbers means that the numeral representations of numbers are unique. And this is sort of a rule about the structure of numbers. So this might be something what I call a syntactic rule about numbers. And in a certain way, numbers, as you think about them in first grade, are not collections of apples. Numbers are sequences of digits having some rules about how you can form them. Let's say this is a rule, not having superfluous zeros. And the way that numbers behave really is in column form. You have column addition and column multiplication. All of the ways that you interact with the numbers, you sort of interact with them in their digits. And that's a really different picture of numbers. We've removed apples from the picture. Now they're sort of syntactic objects. They're numerals. Well, we're not going to go from this perspective, but what we're going to do is also going to be syntactic. It's going to be sort of a syntactic form of the kindergarten intuition, in the sense that what the numbers are they're going to be collections of symbols. They're going to be symbols in a sequence, which I'm going to call a string. A string is a finite sequence of symbols. So for example, this sentence. And choose a very meta one. So we're not going to found numbers in apples. We're going to found numbers in meaningless symbols. And we're going to really discuss what it means meaningless and how we can think of numbers as perhaps not being meaningless, but as being founded in some larger mathematical context. And so what's cutting to the chase without all of this preamble, I'm going to say what our numbers look like. Our numbers, well, here are some numerals, 0, 1, 2, 3. Our numbers, they're going to be called nats. So by a number, I mean a numeral. But by a nat, I mean something very different. By a nat, I mean the actual objects that we're going to construct and study. Nats are not numbers. They represent numbers, but they mean something very concrete. So I'm going to start with an ostensive definition. I'm going to start by pointing. So what is the number 0? As a nat, it's going to be Z, just the symbol Z. The number 1 is going to be the symbol S of Zs. You can think of Z as 0 and S as the successor. So 1 is the successor of Z. Then 2 is going to be the successor of Z. 3 is going to be the successor of the successor of the successor of Z. Now, there are a lot of brackets, and soon there are going to be, if you look at more numbers, you're going to have a very large number of ending parentheses. There is a reason that I have the brackets, which I'll explain later. It's actually going to be apparent in the first units. And also in the racket programming language, there are a lot of brackets. Well, there are actually parentheses. A bracket is this is a bracket, a parenthesis is this. So those aren't brackets, they're parentheses, but that's a bit pedantic. Racket has a lot of brackets, has a lot of parentheses, but let's just say the two words are the same. And then I say that you can't have racket without the bracket. Okay, there you're going to learn how to understand parenthesized expressions. When I learned this language in first year university, my brain got rewired to understand expressions with a bunch of nested parentheses. All latent fear of parentheses in this class will be eradicated. Okay, that's a bit of a side tangent there. So this is by definition by pointing as to what a natural number is, right? So why, if you actually think about this, what advantage does this have over the Apple model? In the Apple model, we had an empty basket. Well, we actually had the physical basket. You can think of Z as being the physical basket, and you can think of each S as being an apple, right? Have we really done anything better than the Apple model? Isn't this like, what advantage could this give us, right? So to that question, does anyone actually have arguments as to why this might be better than the Apple model?
If you fill up the basket with apples sequentially, this clearly shows the evolution of the basket apple system. Wait, no. All right.
Well, actually, you did have a point. Well, I mean, you might have. This probably isn't what you meant, but apples are sort of distinct, right? If you start counting apples, which is the first apple that you remove, right?
Oh. Yeah. Because
So that's a bit of a thing. And you can start making conventions like, let's say we remove the heaviest apple first. But then if you want to form a basket with one more apple, you have the question of which apple do you add? In other words, which place in the ordering by weight do you have? And that's sort of ambiguous, right?
so this just like an order.
Yes, so it actually has two very interesting features. On one hand, the S's are ordered. On the other hand, the S's are also indistinguishable. Like this S is the same as this S, but at the same time, this S is first. Now, if we think about this, let's think about removing an S from this basket. So let's say I have, let's just look at the second example, S of Z. Let's say I want to remove an apple. Then I could remove this S and this bracket, and then I get S of Z, or instead, I could remove the other brackets proceeding differently. And the results that I'd get is the same thing, which isn't true for baskets. So here, no matter what apple you remove, you're going to get the same results, but at the same time, there is a preferred apple to remove, the one at the front.
Yeah.
So that's the first argument. It removes a lot of ambiguity in this way. And sort of the two ways in which it removes ambiguity seem mutually contradictory, but they're not. The second thing is that I can found this in set theory. I can found this in mathematics. Now, what do I mean by this? Well, I put a joke in the notes. The joke is a psychiatrist asks their patients, and are these mathematical objects in the room with us right now? Now, okay, so that's a joke. Every mathematician will characteristically answer, yes, mathematical objects exist platonically. Mathematical objects are real objects. I can interact with mathematical objects in physical ways. They're tactile. They're really something like we spend all of our days talking about mathematical objects. Of course, mathematical objects exist in some abstract realm, but they're very real to us. Now, this sounds a bit culty, but so this is called, that idea is mathematical Platonism. All mathematicians are Platonists by heart. But independent of whether you think platonically as mathematical objects or you think of formally as just a language and just symbols, there is still a way to unambiguously talk about symbols in a way that has something that survives through. I don't understand purely non-Platonic positions because you have to have some thoughts and you have to think the thoughts are thoughts. Well, you have to start somewhere in an abstract realm. Anyway, so the second point really branches off into a discussion of set theory, how I can talk about numbers without reference to actual physical existing objects, how we can think of there being some abstract mathematical realm in which it makes sense to talk about numbers, where if I write down the letter 5, if I type a 5 on a computer, and if your eye sees either of those, and the light in your eye represents some form of information, then to a mathematician, all of those are signs referring to the same number. The number 5, for example, exists. My hand is an anatomical physical reference to this abstract number of 5. That sounds very washy, but you can have this. In BAF, or at least in BAF, we say that we have this. So that branches off in two ways. The first is the set theory notes. So this is the lead into the set theory notes, being able to found everything in mathematical objects. And we take that as the guiding question when we start the set theory notes, which I haven't yet posted. And then the second question is, well, ignoring set theory, so I called the first point, again, breaking a thought, is that gnats are highly structured. Okay, so where does the second point go on? We'll consider the question of how to found them in the second module of the live lecture notes, which is where you'll need the set theory input, which we'll probably do on Friday. So I'll post a bit about set theory because we're going to have a set theory argument in class on Friday. But ignoring that, ignoring the set theory foundations, we're going to continue this module by looking at this thing that gnats are highly structured and investigating, well, what does that mean? Also talking a bit about founding them, but we're going to do this at the level of, let's suppose that strings make sense. Let's suppose that we can talk about some universe of strings. Then I am going to talk about informally how you can specify what strings specify numbers of all strings, right? And that question of what strings specify gnats, not numbers, of all strings is really a question about the structure that gnats have as strings. And this high symmetry and this high structure is really what enables us to make a syntactic definition of numbers. Now, syntax is probably the single most important concept in this class. It is not something that I can define directly, but it is something that will emerge through essentially everything that I say. Syntax unifies everything, is an idea in this class, if I can spell it right. Now, the idea of syntax, first off, where does the name come from? Well, Ptolemy has a book. The Persians call it the Almagest, the greatest. And it is a book about astronomy written for the purpose of astrology. So astrology was a very serious science to the Greeks, and Ptolemy, where you sort of have the Greek diaspora living in Persia. And they cared about fortunes. And so as a Greek having some scientific background about Greek astronomy, Ptolemy was essentially hired to work on an astronomical system for the sake of astrology. And then he founded a model of the solar system that survived until Kepler dismantled it. Well, okay. And so the actual other name of this book is Syntaxis Mathematicus Astronomus, or something of the form. And okay, that's I think the first historic instance of syntaxis. But the word itself, its roots come from where? Syn, so that's, I think, a PIE roots meaning together, and then tasin, which is Greek meaning arrangements. So arranging together, or it's the study of structure of things. Syntax, in the way that it happens in like formal languages and in computer science or in philosophy, is that syntax considers form without questions of substance. So syntax doesn't care about what things mean. Syntax tells you that if you have some things, whatever they are, you can put them together in a certain way. It's the rules of composition that don't look at structure. So for example, in English, there's a very famous sentence by Noam Chomsky called "Colorless green ideas sleep furiously." Now, Chomsky wrote this sentence to be as meaningless as possible. So any meaning that you read into this sentence is you're reading it in. And this sentence actually satisfies the rules of being a syntactically valid English sentence. An example of a sentence that does not satisfy those rules are to, I. This doesn't satisfy grammatical rules before any question of meaning can be put into this sentence. You can also, I guess, say a bunch of usual grammatical errors about like conjugation, subject verb agreements, blah, blah, blah. Those could be errors that you could detect without asking what the question means. And those are syntactic errors. Okay, so that was a bit of a preface on what syntax is. That's not a definition. But syntax is rules about compositions that do not care about meaning. It's a very high level description. Right. So let me say one more thing and then I'll end for today. My mother tells me that I'm over time. Okay. Right. So let me just say this final thing. So what is a nat then, syntactically? Well, first off, what can I say? I can say that Z is a nat, right? That's unambiguous. So what is a nat? Now we're going to talk about what is a nat from their structure. Well, one is Z is a nat. And what second rule could I put in order to get all nats? So can anyone guess what the second rule is?
Parentheses S blank close parentheses is not a nat until you define an argument.
Oh, okay. So let's look at like for S of Z. S of Z is a nat, right? Why is it a nat?
A nat because you have the parentheses on
I can't hear you.
It's not because you have the parentheses on the left and then S and Z as a contents inside the parentheses.
Yeah, so that's one thing. So if a nat isn't Z, then it has to be of the form S of something, right? Where you fill this something in with something, right?
Yeah.
But now let's look at, for example, S of S. This is not a nat.
Oh yeah. The something has to be a nat in itself. That's the extra
Yes.
constraint on the argument.
So a nat is either Z or S of a nat.
Yeah.
So let's look at this definition. What is a nat? Z is a nat, and then you have something like if N is a nat, then S of Z is a nat. Whoops. Does that make sense to
You
everyone?
mean S of N is a nat?
Oh, thank you. Good.
So basically, it just has to be like a combination that has a nat in it, right? That it
Yes.
becomes, yeah.
Well, you put an S around a nat and you get another nat.
Yeah. But
Now,
a nat
here-
always has to maintain like the pure form of it in some way.
Yes. Oh, well, okay, I'm not 100% certain what that means, but it sounds right. That's okay, that's a bad thing to say.
Like it has a nat somewhere in it. So it like maintains. I don't know how to.
It has a nat somewhere in it, but also the form of composition, the rules of how you can compose them are that you surround a nat by parentheses and an S, right?
Yeah.
So that's the specific rule of composition. Now, this definition of a nat is sort of cyclic. What is a nat? A nat is S of a nat. So I've defined something in terms of itself. It's sort of self-referential, right? That sounds a bit weird, but actually, I mean, it isn't weird. It isn't weird. These rules tell you what a nat is. And here, this is the final thing that I'm doing and that I'm breaking for today. So what they tell you is two things. You can use these rules. You can use both of these rules. Oh, by the way, does anyone not understand anything about the rules? Okay, so here are the two things. You can show that something is a NAT. And you can also show that something is not a NAT. In other words, if you have something that's a NAT, these rules can let you show that it is. And if you have something that's not a NAT, you can use these rules to show that it isn't. So here I'm going to give an example of something that is not a NAT. It is S of Z 17. And here is something that is a NAT. S of Z, and then, whoops. So why is this a NAT and why isn't this a NAT? How can I show that using the rules?
Well, nats can only contain parentheses S or Z.
Okay,
17.
that argument works, but that argument is not by these rules. I want you to use only these rules, like applications of those rules. So you're right, but let's try and do an argument that applies these rules.
Well, you could assume that it is a NAT.
Yep,
and then
so
show
we're
that it's
doing
not.
this one then. Okay, so we're showing that it's not a NAT. So assume that it is a NAT, right?
Yeah.
Okay, so what then?
Well, then it has to be the S of a NAT. So
Right, why does it have to be S of a NAT?
by one of the rules above.
Well, there are two ways that we can introduce NATs, right? It's either Z or S of a NAT, right? So it's not Z, right?
Yeah.
I guess that's one other step that you have. It is not Z. Why is it not Z? Well, it's literally not Z, right? Okay, continue. Go ahead.
So since we assumed that the whole expression was a NAT, now we can assume that SZ17 is a NAT.
Yes, very good. So if it is a NAT, then it is of the form S of something where that something is a NAT. So now we're assuming that this is a NAT. Okay, continue.
And then we can just apply that same reasoning.
Right. So now we have the conclusion that Z17 is a NAT. And then finally,
Well, it's obviously not a NAT.
yes. Why is it not? Okay, so give the sentence. You're doing perfect, but give the sentence.
Z17.
Yes, why is it not a NAT?
Because it's not a successor of a NAT.
Right, and neither is it Z. Exactly. So a NAT is either Z or the successor of a NAT. This isn't Z. I mean, it's not literally Z just entirely, and it's not the successor of a NAT. So it's not a NAT. So that's, we know that this isn't a NAT, which breaks the assumption that this was a NAT, SZ17 was a NAT, which breaks the assumption that the entire thing was a NAT. So by diving into the structure, this is sort of like the court case. I'm being very aggressive. You tell me that something's a NAT. I say, really? Really? Is it a NAT? Okay, well, if it is a NAT, it's either Z or S of something. Which one is it? And then you say it. And then I say, oh, well, you told me that. Well, is that a NAT? Let me ask again, which rule is it? And so you break down the structure until you get to a whole. So this is sort of like analysis in the sense that you're starting from something that is unknown and you're getting it down to known pieces. You're breaking it up. So very good. So yeah, so we did this argument. Now, sorry, one more thing before we end today. let's prove that this is a NAT, the other one. So this is one side. What's the other side? How do we show that this is a NAT?
We can do something similar in which we can start by considering parentheses s from the outside and work our way in.
Okay,
So that just means by
can you do it from the inside out, please?
Okay. So that means we would have to prove that the base of this NAT, the very foundation of it, parentheses SZ close parentheses, is a NAT.
Okay, so how do you know that?
By the second rule, we know that if n is a NAT, and this n is going to be z in this case, we know z is a NAT by the first rule, then
So yes.
parentheses SZ is a NAT.
Good. And then
we can continue using the second rule by applying parentheses s and then put that into the argument about 3 times total.
Yeah.
And then we should receive the original number.
Perfect. So in this argument, you've built it up. So you're starting from the ground up and you're building this. And I call an argument like this, also good job, synthesis arguments. You don't have to know this distinction. This is just a piece of culture. THES. In philosophy, there's something called the analytic synthetic distinction. In math, this distinction existed until 200 years ago, and now analysis and synthesis can mean anything, including your great aunts. But classically, analysis was starting at something that's unknown and getting down to known pieces, whereas synthesis was starting from known pieces and getting to something unknown. And the way that you remember this is by chemistry, analytic chemistry versus synthetic chemistry. In synthetic chemistry, you have a lab and you have some tools that you can use, some ingredients, some starting molecules. And then you want to synthesize an unknown molecule. Well, you know what the molecule is, but you don't know how to get it. And starting from your known starting points, you get to this molecule that you want to create. So that's synthetic chemistry. Now, what's analytic chemistry? Analytic chemistry is I hand you an unknown mystery vial, and I ask you what is in the vial. And then you use your techniques to eventually find out what's in the vial. That's proceeding from the unknown to the known, whereas synthesis is going from the known to the unknown. Okay, so that's a piece of culture. But yes, so here you can show that something is a NAT by building it up and showing that it is a NAT by the introduction rules. And you can show that it's not a NAT. How? By tearing it into pieces. So in other words, this definition that we had right here, that a NAT is either Z or successor of a NAT, is multifaceted in that it lets us see that things are NATs, things that are NATs are NATs, and things that are NATs are not NATs. And in both cases, we can use these rules to tell that such is the case. So that's going to be my ending point today. Sorry for going a bit over time. Also, as another preface, the beginning of the lecture was something that I've given like this talk several times, but I gave it a while ago. So that was less polished than the rest of this because I was running out of time leading in. The way that I have the rest of the material of the content prepared is the way that I've been doing the actual content of this class. So that is going to be the level at which we're going to be discussing. If anyone has any feedback, please tell it to me. Also, what do people think of both parts of this lecture? I'd also be interested in hearing that.
Do we have homework to do this week?
Yes, good question. So yes, you do. But the homework is going to use things that we use on Wednesday. Since this is a 5-week class, for example, half of the semester goes by in 2 and a bit of a week. All of the homework that I assign is going to be individual problems due on separate days. So we're going to have homework due on more days of the week than not. Now, because I didn't get to the thing, in fact, it's not even in the notes, the thing that I need to start doing the homework, the first homework assignment is going to be due on Friday. On Wednesday, we're going to discuss proofs, and then on Friday, you are going to be asked to write a single proof. Well, maybe it's going to have a lemma inside of it. But it's going to be a single pointed problem. And then from Friday onwards, we're going to have like 1 problem due every day to 2 days. But they're going to be small bite-sized pieces. I'm also going to add you all to the online submission system. When we're going to have coding assignments eventually, it's going to grade your code automatically and instantly tell you whether you got the problem right or not, and you're going to be allowed to resubmit as many times as you want. So in other words, you know if your code's right or wrong, and you can just keep doing it until you get right code. For the hand graded proofs, well, okay, you're going to have to wait for hearing feedback on me. But there are going to be 3 styles of proofs that we do. Like I said at the beginning in the outline, 3 different types of proofs. With this material, there are going to be like sort of half formal proofs. The proofs are going to be very procedural. They're going to look very structured. In fact, I'm going to ask you to write the proofs in a text document, a plain text document with no formatting, just to highlight like the pure sheer form of the arguments. After that, a lot of the arguments that we're going to do, the proofs that you're going to write, are going to be informal proofs. And I'm going to teach you how to typeset proofs like that using LaTeX. But like it's just paint by numbers. You just type in the arguments, and then I'm going to teach you how to put in math.
Okay.
So I don't understand LaTeX. You don't have to understand LaTeX. All mathematicians generally don't understand this. They just modify things tinker with things until it works.
Got it.
So those are going to be the more free form and super informal arguments. And then finally, at the end of the class, we're going to get to formal arguments. And formal arguments, your computer will be able to verify if they're correct. So you're eventually going to be able to tell a computer, make computer readable proofs using software, read by software that you write in part. And I promise you that we can get to this point. I'm going to gently like ramp it up until we get there. That's the goal. Oh, and as for set theory homework, it's probably going to start being due at the weekends. I'm going to tell you probably tomorrow how to start with the set theory material. Also, please ask me any questions about homework, and please send me anything. So from this point on, most of the material in the class, except for possibly the beginning of the second lecture, is going to be very concrete. And the problems, you're not going to know everything that you need to go into the problem, and there's going to be a lot of problem solving required, but the problems are meant to teach you the problem solving. So please persevere. I promise you, well, if you point out any issues to me, I will do my best to ensure that like you get to a level where you find this course very valuable, and it actually does teach you a lot about math and computer science. The classes that I took in first year, the advanced section classes taught by people who put a lot of work into the class, I still remember the content of those classes. Many years later, I don't do this for not for most classes, but for very special ones which form the basis of the rest of my understanding. Such a class has a possibility of really serving as a good foundation. So that's what I'm trying to deliver. So I want you all to learn how to think abstractly, and hopefully we're going to get there by the end. Right, so that was the first lecture. See you on Wednesday at this time, and then probably I'll send you the set theory notes tomorrow, and you can start looking at them. But I'm probably going to have some set theory homework due on Saturday, with the first other problem being due on Friday. And then we have lectures on Wednesday and Thursday. See you on Wednesday.
See you.
Hi, Professor.
Okay, closing the video. Hopefully that was enjoyable. Bye.